Have you ever imagined a star so small you could walk around it in a day, yet so dense that a single teaspoon of its material would outweigh Mount Everest? Now, imagine that star not sitting quietly in the darkness of space, but spinning at breakneck speeds, emitting beams of energy so powerful they could outshine entire solar systems if only for a flicker in time. What if I told you that lurking among the ancient graveyards of our universe, these objects, white dwarf pulsars, are rewriting what we thought we knew about the life and death of stars? If that feels impossible, it's only because we've barely scratched the surface of the cosmos' most hidden secrets. There's a reason even seasoned astronomers freeze in awe when discussing these bizarre hybrids between white dwarfs and pulsars. The question isn't just, what are white dwarf pulsars? It's, why are they even possible at all? And what terrifying cosmic truths are they hinting at about the fate of our own sun, or the hidden forces governing reality itself? By the end of this journey, you might realize that the universe isn't just stranger than we imagine, it's stranger than we can imagine. But before we continue, subscribe to the channel so you don't miss out on any of these videos. To understand white dwarf pulsars, we first need to understand the players involved, white dwarfs and pulsars. A white dwarf is the final evolutionary state of stars not massive enough to end their lives as neutron stars or black holes. Think of stars like our Sun, or slightly larger ones. Once they exhaust their nuclear fuel, they shed their outer layers into beautiful planetary nebulae, leaving behind a dense, Earth-sized core, the white dwarf. Despite their small size, white dwarfs are monstrous in mass, often packing around 0.6 to 1.4 solar masses into a body roughly the size of Earth. If the mass of the progenitor star isn't enough to overcome electron degeneracy pressure, the quantum mechanical force that prevents electrons from being squashed together, then the star stabilizes as a white dwarf instead of collapsing further into a neutron star or black hole. Their temperatures at formation are searing, often reaching over 100,000 Kelvin, but over billions of years, they cool and fade, becoming cold, dark relics, black dwarfs. However, this cooling process is exceedingly slow. The universe is not yet old enough for any black dwarfs to exist. On the other hand, pulsars are neutron stars that emit beams of electromagnetic radiation out of their magnetic poles. As they spin, these beams sweep across the cosmos like cosmic lighthouses. When the beam crosses our line of sight, we detect a pulse, hence the name pulsar. Neutron stars are formed from stars much more massive than those that become white dwarfs. During their cataclysmic deaths, supernovae, the core collapses so violently that protons and electrons merge into neutrons, creating one of the densest forms of matter known outside of black holes. For decades, the understanding was clear: pulsars are neutron stars, white dwarfs are cooling stellar embers. But reality, as it so often does, found a way to blur these neat boundaries. In the early 21st century, astronomers stumbled upon a phenomenon that defied this clean categorization: white dwarfs acting suspiciously like pulsars. The first confirmed white dwarf pulsar, AR Scorpii, sent shockwaves through the astronomical community when it was discovered in 2016. Located about 380 light-years away, AR Scorpii is a binary system where a white dwarf and a red dwarf dance a deadly tango. But what made AR Scorpii so remarkable wasn't the dance. It was the fact that the white dwarf was pulsing, and not just gently. It was emitting beams of radiation across the electromagnetic spectrum, from radio waves all the way to visible light, and it was spinning with breathtaking speed, completing a full rotation every 1.97 minutes. That might sound slow compared to neutron star pulsars, which can rotate hundreds of times per second, but for a white dwarf, an object thousands of times larger and less dense, this is utterly insane. To picture the magnitude, imagine spinning a bowling ball on your finger fast enough that its outer surface blurs like a helicopter rotor. Now make the bowling ball the size of Earth, made of solidified carbon and oxygen under immense pressure, and spinning without tearing itself apart. That is the reality of a white dwarf pulsar. The implications of AR Scorpii's discovery were profound. It meant that magnetic fields strong enough to cause pulsar-like emissions could exist in white dwarfs, not just neutron stars. In AR Scorpii's case, Its magnetic field strength is estimated to be around 500 million Gauss, about 100 million times stronger than Earth's magnetic field. This immense magnetic field channels energetic particles along its magnetic poles, accelerating them to near light speeds, and producing beams of synchrotron radiation as they spiral along the field lines. What's more mind-bending is the mechanism behind the pulsations. Unlike neutron star pulsars, where rotational energy is the primary driver of emission, white dwarf pulsars like AR Scorpii seem to tap into an intricate interplay between rotational energy, magnetic field interactions, and accretion processes from their companion stars. In AR Scorpii's case, it's believed that the white dwarf is whipping the red dwarf's stellar wind into a frenzy, sparking intense emissions every time the beam sweeps past. But why are white dwarf pulsars so rare? Part of the reason is the sheer extremity of conditions required. You need a white dwarf spinning extremely fast, with an exceptionally strong magnetic field, and you need a companion star close enough to feed the white dwarf material, or at least interact magnetically, but not so close that it triggers a runaway nova or full accretion-induced collapse into a neutron star. It's a tightrope walk on cosmic scales, and the universe doesn't often arrange such delicately balanced configurations. Adding another layer to the enigma is the question of how these white dwarfs achieve their rapid spins. In AR Scorpii's case, astronomers believe that the white dwarf might have once been part of a more typical accreting binary system, drawing in matter from its companion for millions or billions of years. As it pulled in mass, conservation of angular momentum caused it to spin faster and faster, similar to how a figure skater spins more rapidly when pulling their arms inward. Once mass transfer slowed or stopped, the white dwarf remained spinning rapidly, now exposed as a magnetic, beam-emitting monster. There's an eerie poetry to it. A star that should be quietly cooling into oblivion instead finds itself resurrected in a frenzy of magnetic violence, a cosmic revenant that refuses to fade quietly into the dark. Astronomers are now scouring the skies for more white dwarf pulsars, and tantalizing candidates are emerging. Each new discovery challenges our understanding not only of stellar evolution but also of magnetic field generation, binary interactions, and even fundamental questions about matter under extreme conditions. The magnetic fields in white dwarf pulsars are of particular interest because they provide a kind of missing link in our models of stellar magnetism. White dwarfs were known to have strong magnetic fields, but AR Scorpii and its can demonstrate that under the right circumstances, those fields can become organized and dynamic enough to produce coherent, lighthouse-like beams, something previously thought to be exclusive to neutron stars. This forces a re-examination of the so-called magnetic dichotomy among white dwarfs. Why do some white dwarfs have weak fields, while others have fields reaching hundreds of millions of Gauss? Did they inherit these fields from their progenitor stars, or were they generated during the white dwarf formation process itself? Could binary interactions play a role in amplifying magnetic fields post-formation? Each white dwarf pulsar discovered peels back another layer of mystery, but also reveals how much deeper the cosmic rabbit hole goes. And then there's the haunting question: could our own sun, far in the future, follow a similar path? The sun will eventually become a white dwarf, billions of years from now. Although it lacks a binary companion, could there be undiscovered pathways for solitary white dwarfs to develop pulsar-like behavior? Could the remnants of humanity, eons from now, look to the sky and see Sol itself beating like a ghostly heart across the cosmos? White dwarf pulsars represent one of the rarest and most peculiar outcomes in stellar evolution. For decades, astronomers believed that once a star ended its life as a white dwarf, it would simply cool and fade away into obscurity. It was thought that these stellar remnants, stripped of the nuclear fire that once fueled them, would drift silently through the cosmos, slowly becoming colder, dimmer, and utterly inconsequential in the grand drama of the universe. Yet the discovery of white dwarf pulsars shattered this simple narrative, revealing that under the right conditions, even a dead star could ignite a new, astonishing form of cosmic life. To understand the gravity of this revelation, it is important to first appreciate the immense contrast between a typical white dwarf and a pulsar. White dwarfs are remnants of medium-sized stars, stars that, like our Sun, have burned through their nuclear fuel and shed their outer layers. What is left behind is an Earth-sized core composed mostly of carbon and oxygen, held up against gravitational collapse by the strange quantum mechanical effect known as electron degeneracy pressure. Without the ability to sustain fusion reactions, a white dwarf should simply glow faintly for billions of years before eventually cooling into a cold, dark black dwarf. Pulsars, on the other hand, are traditionally thought to arise from an entirely different process. When a massive star, far larger than the Sun, reaches the end of its life, it undergoes a catastrophic supernova explosion. The core that remains collapses into an incredibly dense neutron star, composed almost entirely of neutrons. These neutron stars can rotate at incredible speeds and possess magnetic fields trillions of times stronger than Earth's, shooting beams of radiation from their magnetic poles. As the neutron star spins, these beams sweep across space, and if one of them crosses Earth's line of sight, it appears as a regular pulse of energy, hence the name pulsar. In the traditional view, white dwarfs and pulsars belong to two separate destinies, quiet fading versus explosive rebirth. But white dwarf pulsars show that nature is not bound by our neat categories. Under extreme conditions, a white dwarf can also behave like a pulsar, emitting powerful beams of electromagnetic radiation as it spins rapidly, anchored by a magnetic field millions of times stronger than that of a typical white dwarf. It defies the expected script, acting instead as a cosmic lighthouse long after its nuclear heart has gone cold. The first discovery that brought white dwarf pulsars into scientific awareness was AR Scorpii, a binary star system located about 380 light-years from Earth in the constellation Scorpius. In 2016, astronomers announced that they had observed pulses of radiation coming from this system at regular intervals, every 2 minutes. At first, it seemed like the telltale signature of a neutron star pulsar, but as the observations deepened, an astonishing truth emerged. The object emitting these pulses was not a neutron star at all. It was a white dwarf, spinning rapidly and generating bursts of radio, optical, ultraviolet, and X-ray radiation. It was a phenomenon never before seen in the known universe. The existence of AR Scorpii opened up a flood of new questions. How could a white dwarf spin so fast? How could it generate a magnetic field powerful enough to drive pulsar-like emissions? What mechanism could be powering such intense beams of energy? And perhaps most intriguingly, how many more such objects might be hidden among the stars, their pulses too faint or too infrequent for our instruments to detect? To spin at the rates necessary to mimic a pulsar, a white dwarf must undergo a period of significant angular momentum transfer. This is often achieved in a binary system where a white dwarf accretes matter from a companion star. As the matter spirals inward, it forms an accretion disk, transferring its angular momentum to the white dwarf and causing it to spin up, much like a figure skater pulling in their arms to spin faster. Over time, the accreted matter can also amplify the magnetic field of the white dwarf, creating the necessary conditions for powerful radiation emission. In the case of AR Scorpii, the white dwarf is paired with a cool red dwarf companion. The white dwarf's intense magnetic field accelerates particles away from the companion star to near the speed of light, and these high-energy particles emit radiation across the electromagnetic spectrum. The result is a pulsar-like system powered not by the crushing density of a neutron star but by the magnetic dynamo of a supercharged white dwarf. This discovery forced astrophysicists to reevaluate long-standing assumptions about magnetic field generation in stellar remnants. Traditionally, magnetic fields in white dwarfs were thought to decay over time. The presence of a strong magnetic field in an old white dwarf suggests that under certain circumstances, magnetic fields can not only persist, but even intensify long after a star's death throes have ended. Moreover, white dwarf pulsars provide a unique laboratory for studying extreme physical processes. Their comparatively larger size, relative to neutron stars, and lower gravitational fields make them less hostile environments to model and simulate. Yet, despite being less extreme than neutron stars, they still push the limits of known physics, especially in the behavior of plasma and strong magnetic fields, the mechanics of particle acceleration, and the emission of radiation across a wide range of frequencies. The implications of these systems extend beyond pure academic curiosity. Understanding white dwarf pulsars could shed light on a variety of astrophysical phenomena, from the evolution of magnetic fields and stellar remnants to the mysterious mechanisms behind other cosmic transients like fast radio bursts, FRBs. Some researchers speculate that objects similar to white dwarf pulsars might even contribute to the population of unidentified radio sources peppered across the galaxy. As research deepens, it becomes clear that AR Scorpii might just be the tip of the iceberg. Other systems, currently classified as cataclysmic variables or intermediate polars, might harbor white dwarf pulsars hiding in plain sight, their signatures masked by the complex interactions of binary dynamics and accretion processes. Improved observational techniques, such as more sensitive radio telescopes and multi-wavelength surveys, could reveal an entire hidden population of white dwarf pulsars, reshaping our understanding of the endpoints of stellar evolution. One of the most fascinating aspects of white dwarf pulsars is how they challenge our notions of what it means for a star to die. In the traditional sense, death implies inactivity, a fading into stillness and darkness. But white dwarf pulsars show that death can be a transformation rather than an end. They reveal that even after a star's nuclear engines shut down, under the right conditions, new kinds of activity can emerge, activity that is dynamic, energetic, and astonishingly complex. The physics behind these systems is a rich tapestry woven from many threads: electromagnetism, quantum mechanics, plasma physics, and general relativity. Each observation of a white dwarf pulsar peels back another layer of this cosmic onion, revealing new depths of complexity and wonder. It invites us to question what other, dead objects in the universe might be hiding unsuspected forms of life, not biological life, but the life of motion, magnetism, and light. In a broader cosmic context, the discovery of white dwarf pulsars underscores a profound truth about the universe. It is always more imaginative than we are. Just when we think we have categorized and explained its contents, it surprises us with phenomena that defy expectations and stretch the boundaries of human understanding. In the eerie pulses of light from a white dwarf thousands of trillions of miles away, we hear not the death rattle of a star, but its whispered defiance against oblivion. Even now, as we peer deeper into the night with ever more sensitive instruments, the full story of white dwarf pulsars is only beginning to unfold. The more we learn, the more questions arise. Could white dwarf pulsars eventually spin down and collapse into neutron stars under certain conditions? Could the intense magnetic fields they generate influence the behavior of nearby space, perhaps even warping spacetime itself on tiny scales? Are there evolutionary pathways involving white dwarf pulsars that we have not even conceived of yet? The journey into the heart of these enigmatic objects is far from over. Each new discovery promises not only answers but new mysteries. Mysteries that will challenge generations of astronomers, physicists, and dreamers to come. Binary star systems provide the perfect environment for extraordinary stellar transformations. When two stars are locked together in a gravitational dance, their interactions can dramatically alter the fate of each companion. In the case of white dwarf pulsars, the white dwarf does not simply remain passive. Instead, it often finds itself pulling material from its neighboring star. This accretion process is not gentle. It is a violent, furious siphoning of mass, during which the white dwarf grows heavier and its rotation accelerates. Over time, if the magnetic fields are strong enough and the spin becomes fast enough, the white dwarf can evolve into a pulsar, emitting beams of electromagnetic radiation just like its more famous neutron star cousins. The idea that a white dwarf could behave like a pulsar was once considered nearly impossible. Pulsars were thought to be exclusive to neutron stars, whose incredible densities, packing more mass than the Sun into a sphere barely 20 kilometers across, allowed them to rotate hundreds of times per second and generate fierce magnetic fields. White dwarfs, much larger and less dense, were not expected to achieve the conditions necessary for pulsar-like behavior. Yet nature, in its infinite capacity for surprise, found a way. One of the most striking aspects of white dwarf pulsars is their magnetic field. While most white dwarfs have relatively modest magnetic fields compared to neutron stars, some rare specimens boast fields tens of millions of times stronger than Earth's. These powerful fields, combined with rapid rotation periods, sometimes as fast as a few minutes per revolution, enable white dwarfs to produce coherent beams of radio waves, X-rays, and other emissions. As the white dwarf spins, these beams sweep across space like a cosmic lighthouse, creating the characteristic pulsing signals that define a pulsar. The discovery of the first confirmed white dwarf pulsar, known as AR Scorpii, was a landmark moment in astronomy. In 2016, a team of astronomers observed a peculiar binary system where the white dwarf companion was emitting regular, powerful pulses of radiation across multiple wavelengths. This behavior mirrored that of neutron star pulsars but originated from a star with a far larger radius and lower density. The realization that a white dwarf could produce such pulsations forced scientists to rethink their models of stellar magnetic activity, angular momentum, and radiation mechanisms. AR Scorpii is an especially fascinating system because it represents a kind of cosmic dynamo. As the white dwarf spins, its intense magnetic field interacts with the atmosphere of its red dwarf companion, accelerating electrons to nearly the speed of light. These relativistic particles then spiral along magnetic field lines, emitting synchrotron radiation that we detect as pulses. This mechanism is fundamentally similar to that of a neutron star pulsar but operates on a different scale, with lower energies and longer periods. The existence of white dwarf pulsars raises profound questions about the nature of magnetic fields and stellar remnants. How do these fields originate, and why are they so strong in certain white dwarfs? One possibility is that the magnetic field is a relic of the progenitor star, amplified during the contraction phase as the star shed its outer layers and collapsed into a white dwarf. Another theory suggests that the magnetic field can be enhanced during the accretion process in a binary system, as in falling matter twists and stresses the star's magnetic field lines. Moreover, the study of white dwarf pulsars provides critical insights into the ultimate fate of binary star systems. Over time, as mass transfer continues, the white dwarf can grow close to the Chandrasekhar limit, the maximum mass a white dwarf can have before collapsing under its own gravity. In some cases, this leads to a Type I supernova, a thermonuclear explosion that completely obliterates the white dwarf. In other scenarios, especially where mass accretion is not sufficient to trigger a supernova, the system may evolve into an exotic configuration, such as a double white dwarf binary or even a merger event that forms a neutron star. Beyond their importance in stellar evolution, white dwarf pulsars are also astrophysical laboratories for testing fundamental physics. Their unique properties allow scientists to probe the behavior of matter under extreme magnetic and gravitational fields, study the emission mechanisms of relativistic particles, and even test theories of general relativity. Because their emissions can be precisely timed, much like those of neutron star pulsars, they offer a natural clock that can be used to measure orbital dynamics, gravitational wave emission, and other phenomena. As research continues, more candidate white dwarf pulsars are being identified, although they remain exceedingly rare compared to neutron star pulsars. Each new discovery expands our understanding of the diverse outcomes of stellar death and underscores the complex interplay between mass, magnetism, and angular momentum in shaping the fates of stars. The very existence of white dwarf pulsars forces us to confront the staggering versatility of nature's engineering. It reveals that even in death, stars can find new ways to shine, to pulse, to broadcast their presence across the void. The white dwarf, once thought to be a silent, cooling ember, instead becomes a beacon, a survivor refusing to go quietly into the cosmic night. This defiant persistence echoes a broader theme across the universe, that death is often not an end but a transformation. Just as galaxies collide and birth new generations of stars, just as black holes churn and shape the fabric of space-time itself, so too do white dwarfs, under the right conditions, transcend their expected fate. They blaze with renewed vigor, their pulses marking the rhythm of rebirth on a galactic stage. As we peer deeper into the cosmos, with telescopes that can capture the faintest whispers of ancient light, we will undoubtedly uncover more white dwarf pulsars. Each one will tell a story not just of stellar death, but of resilience, of the relentless drive of energy and matter to find new forms, new expressions, even in the most unlikely circumstances. The quest to understand white dwarf pulsars is far from over. With every new observation, every fresh discovery, we peel back another layer of mystery surrounding these enigmatic objects. Their study holds the potential to unlock answers to some of the most profound questions we can ask. How do stars live and die? What are the ultimate limits of magnetic and gravitational forces? How does the universe recycle its matter and energy across cosmic timescales? White dwarf pulsars remind us that even the quietest corners of the cosmos can hide dynamism and drama beyond anything we can easily imagine. They are monuments to the hidden potential within apparent finality, proof that in the universe, nothing truly ends, everything merely changes. The discovery of the first confirmed white dwarf pulsar, known as AR Scorpii, fundamentally transformed our understanding of stellar remnants. Situated approximately 380 light-years away in the constellation Scorpius, AR Scorpii is a binary system where a white dwarf orbits in close proximity to a red dwarf companion. Unlike anything previously observed, the white dwarf in AR Scorpii emits powerful flashes of radiation every 1.97 minutes, across the entire electromagnetic spectrum, from radio waves to visible light and even into the ultraviolet. This extraordinary behavior immediately captured the attention of astronomers around the world, raising urgent questions about how such an object could exist. In AR Scorpii, the white dwarf's magnetic field acts like an immense cosmic dynamo, accelerating particles to near-light speeds and flinging them outward in beams of energy. As the white dwarf spins, its magnetic axis is not aligned with its rotational axis, causing these beams to sweep across space. Whenever one of the beams points toward Earth, it creates a detectable pulse, much like the flashing light from a distant, cosmic lighthouse. However, unlike traditional neutron star pulsars that primarily emit in the radio band, AR Scorpii's emissions cover an unusually broad range of frequencies, making it one of the most dynamic and intriguing objects in the night sky. The mechanism driving these emissions is a complex interplay of magnetic fields, rotation, and accretion dynamics. It is believed that the white dwarf is stealing material from its red dwarf companion, although in a much less efficient manner compared to typical accreting systems like cataclysmic variables. Instead of forming a luminous accretion disk, much of the infalling material appears to be channeled along the magnetic field lines, creating intense hotspots and accelerating particles directly into the white dwarf's magnetosphere. This process allows the white dwarf to sustain its pulsar-like activity without the need for a traditional disk of swirling gas and plasma. What makes white dwarf pulsars even more fascinating is the enormous gap they bridge between different types of stellar remnants. While neutron star pulsars are tiny, compact, and rotate at incredible speeds, some spinning hundreds of times per second, white dwarf pulsars operate on much slower timescales, often rotating every few minutes to hours. Yet despite their comparatively leisurely spins and larger sizes, their emissions can be just as intense and, in some cases, even more varied across different wavelengths. This forces astronomers to reconsider long-held beliefs about the kinds of objects capable of pulsar behavior. Moreover, the sheer existence of white dwarf pulsars suggests that the boundary between different classes of astronomical objects is far more porous than previously thought. Stars do not fit neatly into rigid categories but instead display a breathtaking diversity in their deaths and afterlives. The implications of this are profound, as they hint at a far richer and more complex cosmic ecosystem than models had previously accounted for. Another critical aspect to consider is the magnetic braking effect experienced by white dwarf pulsars. As they emit beams of radiation, they lose rotational energy, causing them to gradually slow down over time. This process is similar to what happens with neutron star pulsars but occurs on a different scale. Understanding the rate at which white dwarf pulsars lose their spin could offer invaluable insights into magnetic field evolution, binary star dynamics, and even the ultimate fate of such exotic objects. White dwarf pulsars also raise tantalizing possibilities regarding the end states of binary systems. In some scenarios, the white dwarf could continue to accrete mass until it approaches the Chandrasekhar limit, the maximum mass a white dwarf can sustain before collapsing under its own gravity. If this occurs, it could trigger a Type I supernova, one of the most powerful and luminous events in the universe, or it might instead form a neutron star directly through accretion-induced collapse. This potential pathway adds a new wrinkle to our understanding of supernova progenitors and the life cycles of stars. Observations of systems like AR Scorpii are challenging yet incredibly rewarding. Because the pulses occur on relatively short timescales, every few minutes, astronomers must use high-speed photometry and spectroscopy to capture the subtle variations in brightness and spectral lines. These observations require coordination across multiple wavelengths, utilizing radio telescopes, optical observatories, and even space-based ultraviolet and X-ray instruments to build a comprehensive picture of the object's behavior. Beyond AR Scorpii, the hunt is now on for other white dwarf pulsars lurking within our galaxy. Astronomers are scouring survey data, looking for telltale signs of periodic variability that might hint at a spinning, magnetized white dwarf. Each new discovery has the potential to unlock fresh secrets about the magnetic fields, rotation speeds, and evolutionary histories of these enigmatic stars. Finding more white dwarf pulsars could also help determine whether AR Scorpii is a rare exception or merely the first of a vast, hidden population waiting to be uncovered. White dwarf pulsars also have implications for the study of gravitational waves. Although they are not massive enough to generate detectable gravitational waves on their own, interactions within tight binary systems could, under the right conditions, produce ripples in spacetime. As gravitational wave astronomy continues to advance, it is conceivable that some future detections could involve white dwarf pulsar systems, offering an entirely new way to probe their internal structures and dynamics. From a theoretical standpoint, the existence of white dwarf pulsars pushes the limits of current models of magnetism, plasma physics, and stellar evolution. Scientists must now grapple with questions about how such strong magnetic fields are generated and sustained in white dwarfs, whether through dynamo action during the star's earlier life stages or through mergers and accretion processes. Similarly, understanding the detailed mechanics of particle acceleration in white dwarf magnetospheres could shed light on fundamental astrophysical processes that occur throughout the universe, from the environments around black holes to the jets emitted by active galactic nuclei. The broader philosophical implications are equally profound. In many ways, white dwarf pulsars embody the universe's relentless capacity for renewal and reinvention. They are the ultimate testament to the idea that death in the cosmos is not an end but a transformation, often into something even more strange and beautiful than what came before. These ancient, compact stars defy expectations, continuing to pulse with life long after their nuclear fires have gone out, sending beacons of radiation across the emptiness of space as if refusing to be forgotten. Each flash of a white dwarf pulsar is a reminder that the universe still holds mysteries capable of upending our most confident assumptions. Every pulse challenges us to look deeper, to question more profoundly, and to accept that our understanding of the cosmos is still in its infancy. As telescopes grow more powerful and techniques more sophisticated, the hidden population of white dwarf pulsars will likely come into clearer view, and with them, new chapters in the story of the universe will be written. In the case of AR Scorpii, the accretion process does not proceed in the typical steady manner observed in many other binary systems. Instead, the intense magnetic field of the white dwarf disrupts the inner regions of the accretion disk, channeling material along magnetic field lines directly onto the star's magnetic poles. This interaction supercharges the system, causing violent bursts of energy that contribute to the pulsar-like emissions. The white dwarf's rapid rotation, combined with its strong magnetic field, generates a powerful electromagnetic engine capable of producing radiation across the spectrum. What makes AR Scorpii particularly fascinating is that it challenges long-held assumptions about the limits of white dwarf behavior. For decades, the prevailing wisdom maintained that white dwarfs were relatively inert, slowly cooling embers of former stars. Yet AR Scorpii reveals that under extreme conditions, a white dwarf can be extraordinarily dynamic, outshining and outpowering expectations. This discovery opened the door to the possibility that many more white dwarf pulsars might exist, hidden among the countless binary systems scattered throughout the galaxy, waiting to be detected with the right instruments and techniques. The physics underpinning white dwarf pulsars is intricate and stretches the limits of current astrophysical models. Central to this complexity is the role of magnetism. In most stars, magnetic fields are relatively weak compared to the gravitational forces at play. However, in white dwarf pulsars, the magnetic fields are titanic in scale. Some white dwarfs, particularly those classified as magnetic white dwarfs, possess fields measuring upwards of hundreds of millions of Gauss, far beyond anything experienced on Earth. These magnetic fields are not merely passive features. They actively shape the behavior of matter and energy around the star. The spin-down rates of white dwarf pulsars also provide crucial clues about their inner workings. In pulsars, the gradual slowing of rotation over time is a hallmark of energy loss due to radiation. Observations of AR Scorpii show that it, too, is gradually spinning down, albeit much more slowly than neutron star pulsars. This slow spin-down suggests that white dwarf pulsars operate under different regimes of energy loss and magnetic field interactions, offering a unique laboratory for testing theories of stellar magnetism, rotation, and radiation. Furthermore, the existence of white dwarf pulsars raises profound questions about the end states of stellar evolution. Traditionally, stars with initial masses between about 8 and 10 times that of the Sun were thought to end their lives as neutron stars after supernova explosions, while lighter stars became white dwarfs. But the discovery of white dwarf pulsars suggests that some white dwarfs, under the right conditions, can enter a transitional phase, displaying behaviors once thought exclusive to the most extreme objects in the universe. This blurs the lines between stellar categories and hints at a continuum of stellar remnants far more diverse than previously imagined. Another critical aspect of white dwarf pulsars is their potential role in understanding gravitational waves. While neutron star mergers have already been confirmed as sources of gravitational waves, the merging of two white dwarfs, especially if one or both exhibit pulsar behavior, could produce distinct and detectable gravitational signals. Theoretical models suggest that the intense magnetic interactions and rapid rotations associated with white dwarf pulsars might generate ripples in spacetime, albeit weaker than those from more massive objects. Detecting such waves would not only confirm new aspects of general relativity, but also provide deeper insights into the life cycles of binary systems and the fate of compact objects. The rarity of white dwarf pulsars also poses an observational challenge. Unlike neutron star pulsars, which are often discovered through their strong radio emissions, white dwarf pulsars may emit more weakly at certain wavelengths or display variable behaviors that make them harder to detect. Advances in multi-wavelength astronomy, especially with space-based observatories capable of detecting ultraviolet and X-ray emissions, are critical for identifying and studying these elusive objects. Future missions and ground-based telescopes, equipped with more sensitive instruments, may reveal a hidden population of white dwarf pulsars, transforming our understanding of the Milky Way's stellar population. The theoretical implications extend beyond astrophysics into fundamental physics as well. White dwarf pulsars provide natural laboratories for studying extreme states of matter, magnetic reconnection, particle acceleration, and radiation mechanisms. They offer a bridge between the relatively well-understood physics of conventional white dwarfs and the exotic physics of neutron stars and black holes. Each observation adds a new piece to the puzzle, suggesting that the universe is even more complex and fascinating than previously believed. Moreover, white dwarf pulsars inspire philosophical questions about the nature of death and rebirth in the cosmos. A white dwarf pulsar is, in many ways, a star that refused to die quietly. Stripped of its fusion energy, compressed into a dense, degenerate state, it nonetheless finds a way to roar back into life, its magnetic heart beating across the darkness. It challenges the idea that death is final in the cosmos, showing instead that even in the aftermath of destruction, there can be renewal, energy, and astonishing displays of power. The discovery of systems like AR Scorpii encourages astronomers to revisit existing data with fresh eyes. Many binary systems previously classified as ordinary might, under closer inspection, reveal the telltale signs of white dwarf pulsar activity. Subtle periodicities in brightness, unusual spectral emissions, or unexpected variations in radiation could all hint at underlying pulsar behavior. As observational techniques continue to improve, it is likely that more white dwarf pulsars will be found, each one offering new insights and posing new mysteries. Ultimately, white dwarf pulsars are a testament to the universe's ability to surprise us. Just when scientists think they have understood the life cycle of stars, a phenomenon like this emerges, reminding us that there are still vast territories of knowledge waiting to be explored. These objects not only expand our understanding of astrophysics, but also ignite our imaginations, inviting us to ponder the extraordinary possibilities hidden in the cosmos. Some white dwarfs exhibit surface magnetic field strengths exceeding 100 million Gauss, which is over 1,000,000 times stronger than Earth's magnetic field. These immense fields are relics of the progenitor stars, amplified and preserved during the white dwarf formation process. When coupled with rapid rotation rates, these magnetic fields enable the white dwarf to behave like a gigantic unipolar inductor, a cosmic dynamo capable of accelerating particles to relativistic speeds. As the magnetic field lines whip through space due to the star's spin, they induce electric fields strong enough to strip electrons from nearby matter and accelerate them to near the speed of light. This process leads to the generation of highly focused beams of radiation, which sweep across the cosmos in a regular, clock-like pattern. Observers on Earth detect these beams as rapid, rhythmic pulses of energy, giving the white dwarf its pulsar-like signature. The energy output from such a system is staggering. Even though white dwarfs are less compact than neutron stars, the physics of their emissions are still dominated by relativistic effects and extreme electromagnetic phenomena. The beams themselves can interact with the accretion disk and even with the atmosphere of the companion star, causing additional secondary radiation and complex light curves that astronomers can study in detail. These interactions offer unique insights into plasma physics under conditions impossible to replicate on Earth. Moreover, the white dwarf's intense magnetic field can also lead to the formation of magnetospheres, regions of space dominated by the star's magnetic influence. Within these magnetospheres, particles are trapped and spiral along field lines, emitting synchrotron radiation as they lose energy. This is a hallmark of pulsar systems and further blurs the line between traditional neutron star pulsars and their newly discovered white dwarf counterparts. Understanding white dwarf pulsars like AR Scorpii forces astrophysicists to rethink the end stages of stellar evolution. Traditionally, a star like our Sun was expected to shed its outer layers and quietly cool into a white dwarf, dimming over billions of years. But under the right circumstances, such as a close binary relationship and the inheritance of an enormous magnetic field, a white dwarf can remain a lively, active participant in the cosmic theater for far longer than previously thought. This revelation carries significant implications for our broader understanding of the galaxy. White dwarf pulsars could represent a hidden population of energetic objects, influencing their environments in subtle but important ways. They might shape the evolution of nearby planetary systems, contribute to the complex chemistry of interstellar space, and even affect the dynamics of their local galactic neighborhoods. In addition, the existence of white dwarf pulsars opens up tantalizing possibilities for the study of fundamental physics. Because these stars operate under conditions of extreme magnetism, gravity, and high-energy particle interactions, they serve as natural laboratories for testing theories of electromagnetism, quantum mechanics, and general relativity. By observing the behavior of particles and radiation around white dwarf pulsars, scientists can probe the boundaries of known physics and potentially uncover new phenomena. As telescopes become more powerful and sensitive, the hunt for additional white dwarf pulsars intensifies. Future surveys, especially those in radio, optical, and X-ray bands, may uncover many more examples, each offering a new piece of the puzzle. Every discovery brings us closer to understanding how common these objects are, how they evolve, and what they reveal about the life cycles of stars. The discovery of AR Scorpii was not just a singular moment. It was a doorway into an unexplored realm of astrophysics. With each new observation, the story of white dwarf pulsars becomes richer and more complex, challenging us to expand our models of the universe and reminding us that even in the supposed quietude of stellar death, unexpected miracles can arise. The dynamics within these regions are incredibly violent, with particles colliding, accelerating, and emitting bursts of synchrotron radiation, an exotic form of light produced when electrons spiral around magnetic field lines at nearly the speed of light. This synchrotron radiation is key to the broad-spectrum emissions observed from white dwarf pulsars like AR Scorpii, distinguishing them from more conventional sources of stellar radiation. The environment around a white dwarf pulsar is a battleground of extreme forces. Magnetic pressure competes with gravitational attraction, and the rapid rotation injects centrifugal forces that tear at the star's surroundings. The combination of these factors creates a wildly dynamic system where matter, magnetism, and light engage in a never-ending dance of energy exchange. It is a cosmic laboratory where the laws of physics are pushed to their breaking points, offering invaluable clues about the nature of matter and energy under conditions that no human-made experiment could hope to replicate. In addition to the synchrotron radiation, white dwarf pulsars are also thought to emit cyclotron radiation, another form of electromagnetic emission produced by charged particles spiraling around magnetic fields, though at lower energies than synchrotron radiation. Together, these radiation mechanisms provide a rich tapestry of observational signatures that astronomers can decode to unravel the physical conditions near the star. One of the most astonishing aspects of white dwarf pulsars is their potential longevity. Unlike neutron star pulsars, which gradually slow down and fade over millions of years, white dwarf pulsars may remain active for billions of years. Their larger radii and relatively lower densities mean that their spin-down rates are much slower, allowing them to sustain their pulsing emissions across cosmological timescales. This enduring activity suggests that there may be ancient white dwarf pulsars lurking silently across the galaxy, relics from an era long before Earth even formed. The study of white dwarf pulsars not only enriches our understanding of stellar evolution but also bridges several fields of astrophysics, including plasma physics, magnetohydrodynamics, and high-energy astrophysics. Observing these systems pushes the limits of our instrumentation, requiring telescopes capable of detecting rapid, faint variations across multiple wavelengths. It has prompted the development of new observational strategies and theoretical models designed specifically to capture and interpret the fleeting signals these exotic objects emit. Even more intriguingly, the existence of white dwarf pulsars forces astronomers to reconsider the end states of stars. Traditionally, it was believed that stars below a certain mass threshold would simply end their lives as cooling white dwarfs, slowly fading into black dwarfs over trillions of years. Yet the discovery of pulsar-like behavior in white dwarfs hints at a more energetic and active twilight stage for some stars, one filled with magnetic storms, high-energy radiation, and dramatic interactions with nearby companions. As research continues, scientists are beginning to suspect that white dwarf pulsars may not be as rare as initially thought. Many binary systems once classified as cataclysmic variables, where a white dwarf accretes matter from a companion, may actually harbor pulsar-like white dwarfs whose emissions were simply too faint or too infrequent to be noticed with older technology. With new, more sensitive telescopes coming online, such as the Vera C. Rubin Observatory and the Square Kilometre Array, the next decade promises to be a golden era for the discovery and study of these mysterious objects. The implications extend beyond pure academic interest. Understanding white dwarf pulsars could shed light on the broader life cycles of binary systems, the evolution of magnetic fields in stars, and the ultimate fate of stellar remnants. It may also inform our search for exotic astrophysical phenomena, including gravitational waves and even clues about dark matter, if white dwarf pulsars interact with their environments in ways that current models have yet to predict. As we peer deeper into the cosmos, chasing the fleeting, rhythmic flashes of white dwarf pulsars, we are reminded that the universe is far stranger and more wondrous than we ever imagined. Each discovery peels back another layer of the cosmic onion, revealing new mysteries and inviting even deeper questions. The story of white dwarf pulsars is still being written, and the next chapters promise to be as electrifying as the stars themselves. This incredible lifespan suggests that white dwarf pulsars could be far more common in the galaxy than currently observed, simply hidden among older stellar populations or masquerading as less exotic systems due to the subtlety of their emissions. Our current ability to detect them is limited by the sensitivity of our instruments and the wavelengths we monitor, meaning that many of these fascinating objects could be quietly spinning away in the darkness, undiscovered. The rarity with which we find white dwarf pulsars today is likely a reflection of observational bias rather than true scarcity. Traditional surveys for pulsars have focused primarily on radio wavelengths, optimized for the detection of neutron star pulsars, which often emit strong radio waves. However, white dwarf pulsars like AR Scorpii emit most prominently at optical and ultraviolet wavelengths, meaning that specialized instruments and targeted surveys are necessary to uncover more of them. The discovery of more white dwarf pulsars would have profound implications for our understanding of stellar evolution, binary star interactions, and the ultimate fate of stars like our own Sun. The presence of a powerful magnetic field and rapid rotation in a white dwarf suggests that magnetic braking and angular momentum loss might proceed differently than previously thought, influencing the cooling rates and lifespans of these stars. It also hints that binary interactions could play a far more significant role in the late stages of stellar evolution than the isolated star models typically suggest. Furthermore, the study of white dwarf pulsars could offer new insights into the behavior of matter under extreme magnetic pressures. In the intense environments surrounding these objects, atoms and molecules may deform or align along magnetic fields in exotic ways, leading to unique states of matter not seen elsewhere in the universe. Some theoretical models even predict the formation of magnetic crystals, where matter arranges itself in patterns dictated more by magnetic than by atomic forces. Beyond their scientific intrigue, white dwarf pulsars captivate the imagination because they occupy a strange, transitional space in the cosmic zoo. They are not as mind-bendingly extreme as neutron stars or black holes, yet they are far from the inert remnants that white dwarfs were once assumed to be. They represent a middle ground of cosmic violence, a reminder that the universe is full of subtle complexities and surprises that challenge our categorizations. As astronomers develop more sensitive telescopes and refine their detection techniques, the catalog of known white dwarf pulsars is expected to grow. Each new discovery will serve as a data point helping to illuminate the broader population statistics, magnetic field distributions, and evolutionary histories of these remarkable stars. The next generation of space-based observatories, particularly those capable of ultraviolet and X-ray observations, will be crucial in uncovering the hidden population of white dwarf pulsars scattered across our galaxy. In studying white dwarf pulsars, researchers are not only solving one of the universe's fascinating mysteries but also opening doors to deeper questions about the nature of magnetism, plasma physics, and even the limits of relativity under less extreme but still exotic conditions. Every pulse of light from a white dwarf pulsar is a message across the vastness of space and time, a signal from a star that refuses to quietly fade away. Understanding these states could revolutionize not only astrophysics but also fields like plasma physics, materials science, and perhaps even future energy research, where control over magnetic fields and plasma behavior is essential. In fact, the insights gained from white dwarf pulsars might eventually influence technologies that we haven't even yet conceived, pushing the boundaries of what is possible in terms of energy generation, magnetic manipulation, and even propulsion systems. As astronomers refine their models of white dwarf pulsars, the discovery of their nuances may provide answers to some of the most pressing questions in modern physics. For example, they might help clarify how extreme magnetic fields influence the propagation of light and electromagnetic waves. The question of how magnetic fields interact with radiation has implications for understanding the behavior of light across the universe, including how it travels through the interstellar medium and how it is bent and twisted by the gravitational fields of massive objects. White dwarf pulsars could act as laboratories for these phenomena, offering us a natural setting to test the predictions of general relativity and quantum field theory in extreme environments. Moreover, white dwarf pulsars represent a unique window into the evolution of binary star systems. They provide valuable insights into the fates of stars that end their lives as white dwarfs, particularly in close binary systems where material from a companion star can be accreted by the white dwarf. In some cases, this accretion can lead to dramatic outbursts, such as nova explosions or even supernovae, adding another layer of complexity to our understanding of stellar death. white dwarf pulsars challenge the traditional notion that white dwarfs are passive remnants of stars that have exhausted their fuel. Instead, they suggest that these stars can remain active and dynamic for far longer than expected, with fascinating implications for the evolution of binary systems. For astronomers, the detection of white dwarf pulsars is a task that requires precision, patience, and a deep understanding of stellar physics. These pulsars emit at relatively high frequencies, which means that specialized instruments capable of detecting such emissions are required. Many current surveys still focus on traditional pulsar candidates, like those with strong radio emissions, which can obscure the detection of white dwarf pulsars. As our tools become more advanced and our observational techniques more refined, it is likely that more of these elusive objects will be found, contributing to a broader understanding of stellar remnants and their roles in the cosmos. Additionally, the discovery of more white dwarf pulsars could revolutionize our understanding of the distribution of magnetic fields in stellar remnants. In the larger context of stellar evolution, magnetic fields play a crucial role in shaping the behavior of matter under extreme conditions. The more we learn about how these magnetic fields evolve in white dwarf pulsars, the more we can refine our models of other stellar remnants, like neutron stars and even black holes. These insights can help answer fundamental questions about the life cycle of stars and how their remnants interact with surrounding matter. However, despite the tremendous potential for discovery, there are still many unanswered questions. One of the most intriguing mysteries concerns the exact mechanism behind the rapid rotation of white dwarf pulsars. While we know that these pulsars exhibit extreme rotational speeds, we don't fully understand what drives this rotational energy. Is it the result of angular momentum transfer in a binary system? Could it be linked to the accretion of material from a companion star, or is there a different underlying process at work? The answers to these questions will require a combination of detailed observations, theoretical models, and computer simulations to untangle. Even more perplexing is the fact that white dwarf pulsars exhibit relatively stable and predictable pulsations, unlike some of the more erratic behaviors seen in neutron star pulsars. This stability suggests that the physical mechanisms governing these objects are more predictable and perhaps less influenced by chaotic variables. Understanding why white dwarf pulsars are so stable, despite their extreme magnetic fields and high velocities, could shed light on the fundamental nature of pulsar dynamics and might even have applications for understanding other types of stellar oscillations and behaviors. With each new discovery about white dwarf pulsars, our knowledge of the universe expands, and the complexity of stellar life cycles becomes more apparent. The idea that a seemingly ordinary star can evolve into a pulsar-like object defies the simplistic model of stellar death. Instead, it presents a more nuanced view of how stars behave in the twilight of their existence, reminding us that the universe is filled with unexpected phenomena and hidden wonders waiting to be discovered. The search for white dwarf pulsars is not just a quest to solve an isolated problem in astrophysics. It is part of a larger effort to understand the intricate and interconnected processes that govern the behavior of stars, planets, and galaxies. By exploring the extreme environments around these exotic objects, we may unlock new insights into the nature of matter, the structure of the cosmos, and the forces that drive the evolution of everything in the universe, from the smallest subatomic particles to the largest galactic clusters. As technology improves and our knowledge deepens, we are on the cusp of entering an era where previously undetected white dwarf pulsars are uncovered, and their secrets begin to be revealed. The promise of this discovery lies not only in its scientific value but also in its potential to expand the boundaries of our understanding of the universe. The pulsations of white dwarf stars, faint and distant as they may be, represent the rhythm of the cosmos itself, a cosmic heartbeat that continues to echo through the void, urging us to listen closer, think deeper, and look further into the infinite unknown. The journey to fully understanding white dwarf pulsars is still in its early stages, but with each new discovery, we come closer to grasping the full complexity of these fascinating objects. They are not merely isolated phenomena. They are a key part of the cosmic puzzle, offering vital clues about stellar evolution, magnetic fields, and the fundamental forces that shape the universe. The more we study these pulsars, the more we realize that they are not just remnants of dead stars but dynamic, active players in the cosmic stage, defying conventional expectations and opening doors to new questions and possibilities. One of the most promising areas of future research involves studying the environment around white dwarf pulsars. The intense magnetic fields and high-energy emissions they produce create an environment that is unlike anything found on Earth. In some cases, the material surrounding these pulsars is heated to millions of degrees, creating powerful X-ray and ultraviolet emissions. These emissions offer a glimpse into the behavior of matter under extreme conditions, providing us with valuable data on high-energy physics that cannot be replicated in a laboratory on Earth. For example, as material from a companion star is accreted onto a white dwarf pulsar, the process releases enormous amounts of energy, often in the form of X-rays. These high-energy emissions can be used to study the properties of the accreting material, such as its temperature, density, and composition. Furthermore, the way these emissions vary over time can reveal the dynamics of the accretion process itself, giving us a better understanding of how matter behaves in such an extreme environment. These insights could also have broader applications, such as improving our understanding of the behavior of matter in black holes or neutron stars, where similar high-energy processes occur. Another fascinating aspect of white dwarf pulsars is their role in the broader context of stellar population studies. As mentioned earlier, the magnetic fields of white dwarf pulsars are incredibly strong, and they provide a unique laboratory for studying how magnetic fields evolve in stellar remnants. By examining the distribution of magnetic fields in these objects, astronomers can better understand how magnetic fields influence the evolution of other types of stars, including neutron stars and even black holes. This research could lead to new insights into the role of magnetic fields in shaping the structure of galaxies and the behavior of the interstellar medium. In addition to the physical properties of white dwarf pulsars, their role in binary star systems is another area of intense interest. In many cases, white dwarf pulsars are part of close binary systems, where they interact with a companion star. The interactions between the two stars in these systems can lead to a variety of fascinating phenomena, such as nova outbursts, supernovae, and even the formation of X-ray binaries. By studying the behavior of white dwarf pulsars in these systems, astronomers can gain new insights into the dynamics of binary star evolution and the processes that govern the transfer of material between stars. As technology continues to improve, particularly in the realm of space-based observatories, we can expect to uncover many more white dwarf pulsars in the coming years. The discovery of these objects will not only expand our understanding of stellar evolution, but also provide new opportunities for studying the most extreme conditions in the universe. Future missions like the James Webb Space Telescope, along with upcoming X-ray and ultraviolet observatories, will play a crucial role in uncovering the hidden population of white dwarf pulsars that may be lurking in the dark corners of the galaxy. Moreover, the study of white dwarf pulsars is likely to lead to breakthroughs in other fields of astrophysics as well. For example, the extreme conditions around these objects could provide insights into the nature of spacetime itself. The strong magnetic fields and rapid rotation of white dwarf pulsars make them natural laboratories for testing the predictions of general relativity and quantum mechanics. Studying the effects of these extreme conditions on the behavior of light, matter, and gravity could lead to a deeper understanding of the fundamental forces that govern the universe, perhaps even shedding light on the long-standing mystery of quantum gravity. As we continue to study white dwarf pulsars, we are reminded of the inherent complexity and unpredictability of the universe. These objects are not just cosmic curiosities but are integral to our understanding of the larger processes that govern the evolution of stars, galaxies, and the universe itself. Each new discovery adds another layer to the intricate tapestry of the cosmos, revealing more about the forces that shape the stars and the strange, often baffling behavior of matter in extreme conditions. White dwarf pulsars also represent a beautiful paradox of the universe. On the one hand, they are the remnants of stars that have exhausted their nuclear fuel, yet they remain dynamic and energetic, continuing to emit light and radiation long after their apparent death. In this sense, white dwarf pulsars serve as a reminder that the universe is not static, and that even the remnants of stars hold secrets and mysteries that can only be unlocked through careful observation and study. They challenge our preconceived notions of what is possible, inviting us to reconsider our understanding of life, death, and everything in between. Ultimately, the study of white dwarf pulsars is not just about understanding a particular type of star. It is about unraveling the mysteries of the cosmos itself. By probing the extreme environments around these pulsars, we gain insights into the most fundamental aspects of physics and astronomy. And as we continue to learn more about these incredible objects, we are reminded of the vastness and complexity of the universe, and the endless possibilities for discovery that await us in the night sky. The future of white dwarf pulsar research holds exciting promise. As more and more of these pulsars are discovered, the field of astrophysics will be transformed, offering new insights into stellar evolution, magnetic fields, and the behavior of matter in extreme conditions. With each new discovery, we will move one step closer to understanding the intricate dance of matter and energy that shapes the universe, and perhaps even unlock the secrets of the cosmos that have remained hidden for so long. As we continue to push the boundaries of our understanding, one of the most exciting aspects of white dwarf pulsar research is the potential to uncover new phenomena. While we currently understand the basic mechanics of these objects, how their magnetic fields and rapid rotation cause periodic emissions of radiation, there is still so much to learn about the details of their behavior. For example, scientists are particularly interested in how the interaction between the white dwarf pulsar's magnetic field and the surrounding matter leads to the emission of X-rays and gamma rays. These high-energy emissions could reveal even deeper mysteries about the nature of these pulsars. Another fascinating frontier in the study of white dwarf pulsars involves their potential role in the broader cosmic ecosystem. For years, astronomers have speculated that pulsars, including white dwarf pulsars, may play an important role in the interstellar medium. The intense radiation emitted by these objects can ionize nearby gas and dust, influencing the chemical composition and density of their environment. In fact, this interaction could have far-reaching consequences for the formation of new stars and the evolution of galaxies. By studying how white dwarf pulsars affect the surrounding interstellar material, we could learn more about the processes that drive star formation and galaxy evolution on a much larger scale. Equally important are the discoveries that could be made by examining the behavior of white dwarf pulsars in different environments. While most of the white dwarf pulsars we've observed so far are in relatively isolated regions of the galaxy, there are likely many more hidden within the dense environments of star clusters, galactic centers, or even in the midst of massive stellar nurseries. These environments present unique challenges for astronomers, as the intense gravitational fields and complex interactions between stars and gas can make it difficult to study pulsars in detail. However, as our observational capabilities improve, we will be able to peer deeper into these regions and potentially discover entirely new classes of white dwarf pulsars. The key to unlocking the secrets of these cosmic objects lies in the advancement of both observational technology and theoretical models. In recent years, we've seen tremendous progress in the development of instruments capable of detecting and analyzing the high-energy radiation emitted by white dwarf pulsars. The rise of advanced space telescopes, like the Chandra X-ray Observatory and the upcoming James Webb Space Telescope, promises to provide unprecedented views of the universe at the highest energies. With these tools, astronomers will be able to observe the behavior of white dwarf pulsars with greater clarity than ever before, allowing them to test the limits of current theories and potentially uncover entirely new phenomena. But while technology plays a crucial role in the study of white dwarf pulsars, so too does the development of more sophisticated theoretical models. Understanding the behavior of these objects requires not only a deep knowledge of stellar physics, but also a mastery of complex concepts such as general relativity, magnetohydrodynamics, and quantum mechanics. In order to make sense of the extreme conditions surrounding these pulsars, scientists must continue to refine their models of magnetized, rotating stars and the interaction between radiation, matter, and gravitational forces. Theoretical breakthroughs in these areas could shed light on fundamental questions about the nature of matter and energy, as well as help scientists better predict the behavior of other exotic objects in the universe, such as black holes and neutron stars. It's also worth noting that white dwarf pulsars offer more than just a chance to study stellar remnants. They also provide a unique opportunity to test the limits of our understanding of fundamental physics. For example, the extreme magnetic fields present in these objects may allow us to probe the properties of materials under conditions that are otherwise inaccessible. At the same time, the rapid rotation of white dwarf pulsars can test our understanding of general relativity, particularly in how matter behaves near incredibly dense and highly magnetized objects. By studying the light curves and emissions from these pulsars, scientists may be able to make discoveries that challenge our current understanding of space, time, and gravity. Furthermore, white dwarf pulsars could play a pivotal role in the ongoing search for gravitational waves. These ripples in space-time, predicted by Einstein's theory of general relativity, have been detected from events like the collision of black holes and neutron stars. However, some researchers believe that white dwarf pulsars could also produce detectable gravitational waves, especially when they are part of binary systems. The detection of these waves would not only confirm the presence of gravitational waves generated by white dwarf pulsars but could also open up a whole new avenue for studying these objects through the use of gravitational wave astronomy. Interestingly, some theorists have suggested that the study of white dwarf pulsars could one day offer a way to test ideas about dark matter and dark energy. These mysterious components of the universe remain some of the most profound questions in modern physics. Could the presence of exotic matter, like dark matter, influence the behavior of white dwarf pulsars in ways we have not yet observed? Could their unique radiation signatures contain hidden information about the nature of dark energy? These questions remain speculative for now, but the idea that white dwarf pulsars could offer clues about these elusive phenomena adds yet another layer of intrigue to their study. In addition to their scientific importance, white dwarf pulsars also hold significant cultural and philosophical value. These objects force us to confront some of the most profound questions about the nature of existence. What does it mean for a star to die, but still remain active, emitting radiation across the galaxy? How do the forces of nature drive these objects to behave in such extraordinary ways? White dwarf pulsars challenge our understanding of the life cycle of stars and the universe itself. They invite us to look beyond the familiar and consider the ways in which even the remnants of dead stars can continue to influence the cosmos in unexpected and profound ways. For amateur astronomers and enthusiasts, white dwarf pulsars offer an exciting and accessible entry point into the world of astrophysics. While these objects are challenging to observe due to their small size and faint emissions, with the right equipment and knowledge, it is possible to track their pulses and witness their fascinating behavior firsthand. The discovery of new white dwarf pulsars by amateur astronomers could contribute to the overall catalog of these objects, and may even lead to new breakthroughs in our understanding of their properties. As we look to the future, the study of white dwarf pulsars is poised to remain a vibrant and dynamic field of research. With the continued improvement of observational techniques, the development of new theoretical models, and the dedication of scientists and astronomers around the world, we are sure to make new and exciting discoveries about these enigmatic objects. White dwarf pulsars, once thought to be simple stellar remnants, have revealed themselves to be far more than that. They are key to understanding the universe at its most fundamental level. Their study promises to deepen our knowledge of everything from the birth and death of stars to the most extreme conditions in the universe, shedding light on mysteries that have perplexed scientists for generations. White dwarf pulsars represent one of the most captivating and complex phenomena in the universe. They are more than just remnants of stars. They are living proof of the dynamic and ever-evolving nature of the cosmos. As we continue to explore their many mysteries, we are reminded of how much there is still to learn about the universe, and how the study of even the smallest and most distant objects can lead to profound insights into the forces that shape the stars, galaxies, and everything in between. As we venture deeper into the complexities of white dwarf pulsars, the immense challenges in understanding these objects become more apparent. But with each new discovery, the potential rewards become more exciting and profound. What we do know is that white dwarf pulsars are far from ordinary stellar remnants. They are among the most extreme and fascinating objects in the universe, offering us a rare glimpse into the violent and energetic processes that govern stellar life cycles. One of the most promising areas of research is the connection between white dwarf pulsars and their progenitors. White dwarfs themselves are the end product of medium-mass stars, which have exhausted their nuclear fuel and shed their outer layers. But what about the pulsars that emerge from these remnants? How do the extreme conditions of rapid rotation and intense magnetic fields come into play during this transition? How do these features affect the structure of the star in the long term? And what role do they play in the broader ecosystem of cosmic evolution? While much is still unknown about the origins of white dwarf pulsars, scientists believe that studying their birth and evolution will be crucial for understanding the life cycle of stars more broadly. It is not enough to simply observe these pulsars in their final states. We must trace their journey from the moment they begin to form, exploring the various factors that lead to their rapid rotation and magnetic activity. Only then can we begin to piece together the full narrative of their life cycle, from star to white dwarf pulsar. This understanding could lead to major breakthroughs in our comprehension of other stellar remnants as well. For instance, neutron stars and black holes, two of the most well-studied types of stellar remnants, share many of the same features as white dwarf pulsars, including intense magnetic fields and rapid rotation. However, the differences in their sizes, compositions, and gravitational effects mean that they behave in vastly different ways. Understanding white dwarf pulsars could provide valuable insights into these other cosmic objects, helping astronomers refine their models of how matter behaves under extreme conditions. The importance of studying white dwarf pulsars extends far beyond their role as cosmic oddities. These objects may provide critical information about the fundamental forces of nature. For example, the strong magnetic fields surrounding white dwarf pulsars may allow scientists to test theories of electromagnetism and plasma physics in environments far more extreme than anything found on Earth. As we look at the behavior of these magnetic fields, we could uncover new laws of physics that govern their dynamics, opening doors to new fields of study and new technologies in the process. Moreover, the role of white dwarf pulsars in the galactic environment should not be underestimated. While their small size may seem insignificant compared to massive stars or supernovae, their emissions and interactions with the surrounding matter can have significant effects on their environments. The energy released by these pulsars can alter the chemistry of the interstellar medium, influencing star formation, planetary development, and even the growth of galaxies. Understanding how these objects affect their surroundings is essential for a complete picture of cosmic evolution. As we look toward the future, the development of next-generation telescopes and observational instruments will undoubtedly play a key role in advancing our understanding of white dwarf pulsars. Observatories like the Event Horizon Telescope, which has already provided us with the first images of black holes, are poised to expand our observational capabilities. The next few decades will likely see the advent of new space-based instruments capable of detecting emissions from even the most distant and faint white dwarf pulsars, allowing astronomers to study these objects with unparalleled precision. These advancements in technology will also help to answer some of the more pressing questions about white dwarf pulsars. For example, while we have made great strides in detecting X-rays and gamma rays emitted by these objects, much remains to be understood about the precise mechanisms driving these emissions. Are they caused purely by the interaction of the pulsar's magnetic field with surrounding gas, or is there something else at play? Perhaps a new form of energy, or a novel physical process we have yet to discover? As the search for answers continues, the importance of international collaboration in the study of white dwarf pulsars becomes more evident. Astronomers, physicists, and engineers from around the world will need to work together to develop the tools and techniques necessary to explore these objects in greater detail. Collaborative efforts will also be essential in pooling resources and expertise to interpret the vast amounts of data generated by these observations. The broader scientific community also stands to benefit from the study of white dwarf pulsars. As we deepen our understanding of these objects, we may uncover insights that could have applications in fields far beyond astronomy. For example, the study of extreme magnetic fields could have implications for the development of new technologies, such as more efficient energy storage systems or advanced propulsion methods for space exploration. By pushing the boundaries of our knowledge in astrophysics, we may find practical solutions to some of the most pressing challenges facing humanity. Of course, as with any area of scientific exploration, the study of white dwarf pulsars comes with its share of challenges. The extreme environments surrounding these objects make them difficult to study directly, and their faint emissions can be easily overwhelmed by background noise from other cosmic sources. Moreover, the theoretical models we rely on to explain their behavior are constantly evolving, and there is still much work to be done to refine our understanding of the underlying physics. However, it is precisely these challenges that make the study of white dwarf pulsars so exciting. Each new discovery brings us closer to solving some of the most profound mysteries of the universe. One particularly intriguing aspect of white dwarf pulsars is their potential connection to other exotic objects in the universe, such as magnetars and rotating black holes. Magnetars, which are a type of neutron star, share some similar features with white dwarf pulsars, including their intense magnetic fields. Could there be an underlying connection between these objects? And if so, what does it reveal about the nature of stellar evolution? Similarly, the rapid rotation of white dwarf pulsars may have important implications for our understanding of the rotation of black holes. Are there similarities between these two classes of objects that we have yet to fully explore? These are questions that could push the boundaries of astrophysics and lead to major breakthroughs in our understanding of the universe. As the study of white dwarf pulsars progresses, we may also begin to uncover their connections to other areas of scientific inquiry, such as the search for extraterrestrial life. Pulsars, with their regular emissions and extreme environments, offer a unique environment for the formation of potentially habitable planets. Could white dwarf pulsars be home to distant worlds, or could they influence the development of life elsewhere in the galaxy? While these ideas may seem far-fetched, they remind us of how interconnected the various branches of science can be, and how the study of one cosmic phenomenon can lead to insights in entirely unexpected areas. The future of white dwarf pulsar research is brimming with potential. As technology advances and our understanding of the universe continues to evolve, these enigmatic objects will remain at the forefront of scientific inquiry. With each new observation, each new theoretical model, we come closer to unlocking the secrets of these fascinating objects, and in doing so, we move one step closer to understanding the fundamental nature of the cosmos itself. White dwarf pulsars serve as a testament to the mysteries that still await us in the far reaches of the universe. Their extreme conditions and behavior challenge our understanding of physics, and their study promises to push the boundaries of knowledge in ways we can scarcely imagine. As we continue to explore these cosmic oddities, we are reminded of just how much there is still to discover, and how much more there is to learn about the universe that surrounds us. As we continue to explore the mysteries of white dwarf pulsars, it's important to recognize their potential to unlock new paradigms in astrophysics. These objects, which occupy a unique space in the life cycle of stars, not only offer us a glimpse into the final stages of stellar evolution, but also provide valuable information about the fundamental forces that shape the universe. Their peculiar characteristics and extreme environments make them ideal candidates for testing the limits of our scientific understanding, challenging our existing theories, and opening new avenues for exploration. One of the most intriguing aspects of white dwarf pulsars is the role they might play in the formation of other cosmic structures. For example, the energy and matter ejected by these pulsars can have a profound impact on the surrounding interstellar medium. Their emissions, often in the form of intense radiation, could help shape the environment in which new stars and planetary systems are born. This interaction between pulsars and the interstellar gas could influence the rates of star formation, the distribution of heavy elements in the galaxy, and even the conditions necessary for life to emerge on distant worlds. Additionally, the study of white dwarf pulsars can provide valuable insights into the long-term evolution of galaxies. Pulsars, particularly those in binary systems, are believed to play a role in the processes that regulate the growth of galaxies. The gravitational interactions between pulsars and their companion stars, for instance, can lead to the exchange of matter, transferring material from one star to another. This can ultimately influence the chemical composition of the galaxy, contributing to the enrichment of the interstellar medium with heavy elements. In this way, white dwarf pulsars are not just cosmic oddities. They are active participants in the ongoing evolution of galaxies. The unique properties of white dwarf pulsars also hold potential for understanding the behavior of matter under extreme conditions. For instance, the intense gravitational fields and rapid rotation rates of these pulsars provide a natural laboratory for studying the effects of relativity and quantum mechanics. While scientists have made significant progress in understanding how gravity behaves near massive objects like black holes, the study of white dwarf pulsars offers a different perspective, one that could lead to new insights into the nature of spacetime itself. The rapid rotation of white dwarf pulsars is another feature that sets them apart from other stellar remnants. As these objects spin at incredibly high speeds, often completing one rotation every few milliseconds, they produce beams of radiation that can be detected by telescopes. These beams sweep across the sky in a regular pattern, much like the light emitted by a lighthouse. This rotational behavior provides valuable information about the internal structure of the pulsar and offers clues about the processes that drive its rapid spin. One of the key questions scientists are trying to answer is how white dwarf pulsars achieve such rapid rotation. Unlike neutron stars, which are born with high rotation rates due to the collapse of massive stars, white dwarf pulsars are thought to inherit their rotation speeds from the collapse of less massive progenitors. The process by which they become rapidly rotating remains a subject of intense research. It is believed that the collapse of the white dwarf during its transition into a pulsar could be influenced by the transfer of angular momentum from a companion star in a binary system. This exchange of mass and energy can cause the white dwarf to spin faster, eventually reaching the extreme rotation speeds observed in pulsars. The magnetic fields of white dwarf pulsars also play a crucial role in their behavior. These magnetic fields are typically millions to billions of times stronger than Earth's magnetic field, and they exert a profound influence on the surrounding environment. The interaction between the pulsar's magnetic field and the charged particles in its vicinity can create a variety of phenomena, including powerful X-ray emissions, energetic particle jets, and even shock waves that propagate through the interstellar medium. Interestingly, the magnetic fields of white dwarf pulsars are not static. Over time, they can evolve, shifting in strength and orientation as the pulsar spins. This dynamic behavior makes them an ideal subject for studying the time-dependent nature of magnetic fields in astrophysical contexts. By examining how these fields evolve, scientists can gain a better understanding of the mechanisms that govern the behavior of magnetic fields in other cosmic objects, such as black holes, neutron stars, and even galaxies. The study of white dwarf pulsars also raises important questions about the ultimate fate of these objects. Unlike neutron stars, which can eventually collapse into black holes, white dwarfs are not massive enough to undergo such a transformation. Instead, their fate is tied to their ability to maintain their structural integrity. Over time, white dwarf pulsars will gradually lose energy, eventually slowing down and ceasing to emit radiation. This process, known as spin down, occurs as the pulsar loses rotational energy through the emission of electromagnetic radiation. The rate at which a white dwarf pulsar slows down depends on several factors, including the strength of its magnetic field and the amount of matter it interacts with. As the pulsar spins down, it gradually loses its ability to maintain its rapid rotation, and the emissions it produces become weaker. Eventually, the pulsar will cease to emit detectable radiation, becoming what is known as a dead white dwarf. However, this does not mean that white dwarf pulsars simply vanish. In fact, their legacy may continue in the form of their remnants. The final stage in the life of a white dwarf pulsar is the cooling phase, during which it gradually fades from view as it loses its residual heat. Over billions of years, the white dwarf pulsar will continue to cool and shrink, eventually becoming a cold, dark object that can no longer be observed by conventional means. This process of cooling and fading is a natural part of the white dwarf's evolution, and it provides valuable information about the long-term behavior of stellar remnants. Despite their eventual demise, the study of white dwarf pulsars remains one of the most exciting frontiers in astrophysics. These objects offer a unique window into the extreme environments of the universe, and their study promises to yield new insights into the fundamental laws of nature. By continuing to observe and analyze these enigmatic objects, scientists hope to uncover more about the forces that govern the cosmos and, perhaps, even unlock the secrets of the universe's most mysterious phenomena. In addition to their role in the study of fundamental physics, white dwarf pulsars may also play a key role in the search for extraterrestrial life. The unique radiation emitted by these objects could potentially be harnessed by alien civilizations for energy production, or it could serve as a beacon for communication across vast distances. As we continue to explore the possibility of life beyond Earth, understanding the characteristics of white dwarf pulsars may prove to be a crucial step in our quest to understand the broader cosmic landscape. While much remains to be learned about white dwarf pulsars, one thing is clear: these objects are among the most fascinating and complex phenomena in the universe. Their study offers an unparalleled opportunity to explore the mysteries of stellar evolution, magnetic fields, and the fundamental forces that govern the cosmos. With each new discovery, we move closer to unlocking the secrets of these extraordinary objects, and in doing so, we uncover more about the nature of the universe itself. As our understanding of white dwarf pulsars deepens, it may lead to new breakthroughs in our understanding of other areas of astrophysics. From the behavior of matter under extreme conditions to the formation and evolution of galaxies, the study of these objects has the potential to revolutionize our understanding of the cosmos. And as we continue to refine our models and improve our observational techniques, the mysteries of white dwarf pulsars will continue to unfold, offering a glimpse into the hidden workings of the universe. The study of white dwarf pulsars is a rapidly evolving field, one that holds great promise for future discoveries. As scientists continue to push the boundaries of knowledge, these enigmatic objects will remain a focal point of research, offering a unique opportunity to explore the most extreme environments in the universe. Whether through the study of their magnetic fields, their role in galactic evolution, or their potential connection to other exotic objects, the study of white dwarf pulsars will undoubtedly continue to captivate and inspire scientists and the public alike for years to come. As we continue to explore the fascinating world of white dwarf pulsars, it's essential to consider the broader context in which these objects exist. The universe is filled with countless phenomena, many of which are interconnected in ways we are only beginning to understand. White dwarf pulsars, like other types of stellar remnants, are part of the ongoing dance of life, death, and rebirth in the cosmos. Their evolution provides clues not only about the life cycles of individual stars, but also about the dynamic processes that shape entire galaxies. One of the more interesting aspects of white dwarf pulsars is their role in the larger ecosystem of the universe. While these objects may appear isolated or solitary in nature, they are far from it. In fact, white dwarf pulsars are often part of binary or even multiple star systems, meaning that they interact with nearby stars in complex ways. These interactions can significantly alter the behavior and evolution of both the pulsar and its companion stars. For example, in some binary systems, a white dwarf pulsar may be paired with a normal star, which can lead to a process known as accretion. In accreting systems, the pulsar pulls material from its companion star, gradually siphoning off gas and other matter. This material is heated up as it spirals toward the pulsar, often resulting in the emission of X-rays and other high-energy radiation. This process is not only a key feature of many pulsars but also provides valuable insights into the mechanics of accretion and the behavior of matter under extreme gravitational forces. Furthermore, the interaction between white dwarf pulsars and their companion stars can lead to phenomena such as nova outbursts, or even the formation of exotic systems known as cataclysmic variables. These systems, in which a white dwarf pulsar accretes material from a nearby star, can be spectacular sources of energy and light, sometimes outshining their entire host galaxies. The study of these systems provides important information about the life cycles of stars and the complex processes that govern their evolution. While we've primarily discussed the relationship between white dwarf pulsars and their companion stars, it's also important to recognize the role they play in the broader galactic context. Pulsars, in general, are thought to influence their local environments in ways that extend far beyond their immediate surroundings. The radiation and energetic particles emitted by white dwarf pulsars can interact with the interstellar medium, shaping the characteristics of the gas and dust that fills the space between stars. This interaction between pulsars and the interstellar medium is crucial for the ongoing evolution of galaxies. Pulsars are believed to play a role in the process of supernova feedback, which is the mechanism by which the energy released by dying stars can trigger the formation of new stars. As white dwarf pulsars release energy into the surrounding space, they can heat up the gas and dust around them, causing it to expand and spread throughout the galaxy. This can influence the rate of star formation and even the types of stars that are born in a given region of space. Moreover, white dwarf pulsars, like other types of stellar remnants, are thought to contribute to the enrichment of the interstellar medium with heavy elements. When these objects die, they can release vast amounts of material into space, including elements like carbon, oxygen, and iron, key ingredients for the formation of planets and other stars. This process of cosmic recycling ensures that the universe remains a dynamic, ever-changing environment, where the death of one star can give birth to new generations of celestial objects. In addition to their role in galactic evolution, white dwarf pulsars are also valuable tools for studying the fundamental laws of physics. As mentioned earlier, the extreme conditions present in these objects, such as their intense magnetic fields and rapid rotation rates, make them ideal candidates for testing the limits of our current scientific understanding. The behavior of matter under such conditions can provide important clues about the fundamental forces that govern the universe, including gravity, electromagnetism, and the strong and weak nuclear forces. For example, the study of white dwarf pulsars offers a unique opportunity to probe the nature of quantum mechanics and general relativity in extreme environments. These two theories, quantum mechanics, which governs the behavior of particles on the smallest scales, and general relativity, which describes the behavior of massive objects and gravity on larger scales, are currently our best descriptions of the physical world. However, they are notoriously difficult to reconcile, particularly when it comes to objects like black holes and neutron stars. White dwarf pulsars, with their combination of strong magnetic fields, rapid rotation, and unique internal structure, offer a natural testing ground for these theories. By studying how these objects behave, scientists hope to uncover new insights into the way these fundamental forces interact, potentially leading to a more unified theory of physics. This could have profound implications for our understanding of the universe, from the behavior of subatomic particles to the large-scale structure of spacetime itself. In addition to their role in testing fundamental physics, white dwarf pulsars are also of interest to scientists studying the origins of gravitational waves. These ripples in spacetime, first predicted by Einstein in his theory of general relativity, have been detected by observatories like LIGO and Virgo. Gravitational waves are produced by the acceleration of massive objects, such as merging black holes or neutron stars, and provide a unique way to study the most energetic events in the universe. While gravitational waves are most commonly associated with events like the collision of black holes, it is possible that white dwarf pulsars could also produce detectable gravitational waves, particularly in binary systems. As two pulsars orbit each other, they generate ripples in spacetime that could, in theory, be detected by sensitive instruments here on Earth. By studying these potential gravitational waves, scientists can learn more about the behavior of white dwarf pulsars and gain further insights into the nature of spacetime itself. Beyond their scientific value, white dwarf pulsars also raise fascinating philosophical and existential questions. Their extreme nature, spinning at incredible speeds, emitting intense radiation, and inhabiting the final stages of stellar evolution, forces us to confront the boundaries of what we know and understand about the universe. These objects serve as a reminder of the vastness and complexity of the cosmos, and they challenge us to think about our place within it. As we continue to explore the universe and discover new phenomena, white dwarf pulsars will undoubtedly remain at the forefront of scientific inquiry. Their study promises to yield new insights into the workings of the cosmos, and their mysteries continue to captivate astronomers, physicists, and the general public alike. Whether through the investigation of their magnetic fields, the study of their accretion processes, or the search for gravitational waves, white dwarf pulsars offer a wealth of opportunities for discovery. The study of these enigmatic objects is not just about uncovering the secrets of a single type of star. It's about exploring the very nature of the universe itself. White dwarf pulsars serve as cosmic laboratories, where the laws of physics are put to the test in ways that no other objects can replicate. By continuing to study these fascinating phenomena, we can deepen our understanding of the cosmos and unlock the mysteries of the universe that have remained hidden for so long. As we move forward in our exploration of white dwarf pulsars, it's important to take a closer look at some of the specific ways in which these fascinating objects challenge our understanding of stellar evolution, magnetic fields, and even the nature of spacetime itself. Despite their relatively small size compared to other cosmic giants like black holes or neutron stars, white dwarf pulsars pack an immense punch in terms of the insights they can provide into the inner workings of the universe. They bridge the gap between the life of a star and the aftermath of a stellar collapse, serving as a crucial piece of the cosmic puzzle. One of the key aspects of white dwarf pulsars that makes them so intriguing is the role of magnetic fields in their behavior. Magnetic fields are a fundamental component of many astronomical objects, from the sun to black holes, and understanding their structure and influence is a crucial part of modern astrophysics. However, the magnetic fields associated with white dwarf pulsars are unlike those of most other objects in the universe. White dwarfs, by their very nature, are compact remnants of stars that were once much larger and more luminous. After exhausting the fuel in their cores, these stars undergo a series of transformations, eventually shedding their outer layers and leaving behind a dense, incredibly hot core. In the case of a white dwarf pulsar, this core is surrounded by a magnetic field that is often 1,000,000 times stronger than that of Earth. The strength and complexity of this magnetic field have a profound effect on the pulsar's behavior, influencing its rotation, radiation emission, and overall evolution. The magnetic field of a white dwarf pulsar is not just a passive bystander in the pulsar's behavior. It plays a dynamic and active role in shaping the object's characteristics. As the white dwarf pulsar spins rapidly, its magnetic field can become twisted and warped, causing complex interactions between the field and the surrounding plasma. These interactions often lead to the generation of energetic particles, which can accelerate to nearly the speed of light. These particles are then funneled along the pulsar's magnetic poles, where they are emitted as intense beams of radiation. This is why white dwarf pulsars, like their neutron star counterparts, often emit periodic bursts of electromagnetic radiation, including X-rays, radio waves, and even gamma rays. What makes the magnetic fields of white dwarf pulsars even more interesting is their potential to reveal information about the star's interior structure. The behavior of a pulsar's magnetic field can provide valuable clues about the composition and physical properties of the white dwarf's core. For example, the interaction between the magnetic field and the plasma surrounding the pulsar can offer insights into the internal magnetic structure of the white dwarf, which is difficult to observe directly due to the extreme conditions inside these objects. The magnetic fields also offer a way to study the behavior of matter in the presence of intense gravitational forces, making white dwarf pulsars an invaluable tool for testing the predictions of both general relativity and quantum mechanics. Another important area where white dwarf pulsars have the potential to expand our knowledge is in the study of accretion processes. As mentioned earlier, many white dwarf pulsars exist in binary systems, where they interact with a companion star. In some cases, this interaction leads to a process known as accretion, in which the white dwarf pulsar pulls material from the companion star. This material, which is typically composed of gas and dust, is pulled toward the pulsar by its intense gravitational field. As the material spirals inward, it becomes heated to incredibly high temperatures, emitting radiation across a broad spectrum of wavelengths. This accretion process is particularly important because it can reveal key information about the physical properties of the pulsar's surface and the surrounding environment. For example, the accretion of material can cause the pulsar to emit X-rays, which are often detected by astronomers using space-based telescopes. By studying the X-ray emission from white dwarf pulsars, scientists can learn about the temperature, density, and composition of the material being accreted, as well as the dynamics of the accretion process itself. Moreover, the presence of accretion disks around white dwarf pulsars can provide insights into the behavior of matter under extreme conditions. In the case of a binary system, the material in the accretion disk often becomes highly compressed and heated, leading to the formation of intense radiation and energetic particles. These particles can be ejected at high speeds, forming jets of matter that can be observed as powerful bursts of radiation. By studying these jets and the associated radiation, scientists can gain a better understanding of the complex processes that govern the formation and evolution of accretion disks and the objects they surround. As we continue to probe the mysteries of white dwarf pulsars, we must also consider their potential role in the broader context of galactic evolution. While these objects may seem like isolated phenomena, they are often found in environments that are intimately connected to the larger dynamics of galaxies. For example, the energy emitted by white dwarf pulsars can have a significant impact on their surroundings, influencing the behavior of nearby stars and gas clouds. The radiation emitted by these pulsars can also help shape the structure of the interstellar medium, the diffuse gas and dust that fills the space between stars in a galaxy. The energetic particles and radiation produced by white dwarf pulsars can ionize the surrounding gas, leading to the formation of regions of hot, ionized material known as HI regions. These regions are often associated with star-forming areas, when new stars are born from the collapse of gas clouds. In this way, white dwarf pulsars can play an indirect role in the process of star formation, providing the energy needed to trigger the collapse of gas clouds and initiate the formation of new stellar systems. Additionally, the study of white dwarf pulsars has the potential to reveal information about the long-term evolution of galaxies. As pulsars release energy into their surroundings, they can influence the distribution and movement of gas and dust within a galaxy. This energy can help regulate the rate of star formation, affecting the overall population of stars in a given galaxy. Understanding how white dwarf pulsars interact with their environment is crucial for understanding the broader processes that shape the evolution of galaxies over cosmic timescales. One of the most intriguing aspects of white dwarf pulsars is their potential connection to gravitational wave astronomy. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. These waves carry information about the objects that generated them, allowing astronomers to study the most energetic events in the universe. While gravitational waves are most commonly associated with events like the collision of black holes, they can also be produced by the motion of white dwarf pulsars, particularly in binary systems. As two pulsars orbit each other, they generate ripples in spacetime that could, in theory, be detected by sensitive instruments here on Earth. The study of these gravitational waves could provide a wealth of information about the properties of white dwarf pulsars, including their masses, spins, and magnetic fields. Additionally, these waves could offer a unique way to study the behavior of spacetime itself, providing further evidence for the predictions of general relativity. As we continue to learn more about white dwarf pulsars and their place in the cosmos, we must also acknowledge the profound implications their study holds for our understanding of the universe. These objects, while small and seemingly unremarkable in comparison to the larger cosmic giants, offer a unique and powerful window into the laws of physics, the evolution of stars, and the nature of spacetime. By studying these enigmatic objects, we not only uncover the secrets of their own existence but also gain valuable insights into the broader forces that shape the universe itself. White dwarf pulsars, with their complex interplay of magnetic fields, radiation, and accretion, are fascinating objects that push the boundaries of astrophysical research. As we delve deeper into their characteristics, it becomes increasingly apparent that these stellar remnants are not merely leftovers of dead stars, but active, dynamic systems that can provide insights into the very nature of spacetime, matter, and the extreme conditions that govern the universe. One of the most compelling aspects of white dwarf pulsars is their potential to reveal new physics that has yet to be fully understood. The extreme environments within these objects, particularly in their cores, can lead to conditions where our current models of physics break down or are stretched to their limits. This is especially true when we consider the quantum mechanical behavior of particles in the presence of strong magnetic fields and the intense gravitational forces exerted by the white dwarf's dense core. The strong magnetic fields that are characteristic of white dwarf pulsars are particularly interesting from a theoretical standpoint. These fields can affect the way that atoms and subatomic particles behave, altering the usual interactions that govern matter on a macroscopic scale. For example, in a white dwarf pulsar, the magnetic field can cause electrons and other particles to follow curved paths, potentially leading to new forms of particle interactions and behavior. In addition, the high density of the white dwarf's core could allow for exotic states of matter, such as degenerate matter, where the usual laws of thermodynamics and quantum mechanics no longer apply in the traditional sense. One of the theoretical challenges that scientists face when studying white dwarf pulsars is understanding how these objects can sustain such strong magnetic fields over long periods of time. In typical stars, magnetic fields are generated by the motion of ionized gases in the outer layers, but in white dwarfs, much of the gas has been expelled. This leaves behind a dense, degenerate core where the magnetic field could be much more stable and persistent. The precise mechanisms that allow for such a strong and enduring magnetic field in a white dwarf pulsar remain an open question in astrophysics. In order to answer this question, researchers are turning to advanced computational models and simulations to simulate the extreme conditions inside these objects. By modeling the behavior of matter under such conditions, scientists can make predictions about the properties of white dwarf pulsars that could be tested with future observations. For example, future space telescopes or gravitational wave detectors could be used to study the radiation emitted by white dwarf pulsars or to detect the subtle ripples in spacetime caused by their movements. These observations could then be used to refine our understanding of the physical processes at work inside these objects. In addition to their magnetic fields, the accretion process that takes place in binary systems involving white dwarf pulsars is another key area of interest. When a white dwarf pulsar is part of a binary system, it can pull material from its companion star, creating a hot, dense accretion disk around the pulsar. This process not only produces intense radiation but also provides an opportunity to study the dynamics of matter in such extreme environments. One of the most interesting aspects of accretion is how it can change the physical properties of the white dwarf pulsar over time. As material is accreted, it can alter the pulsar's mass, temperature, and magnetic field strength. In some cases, this process can even lead to the formation of a type of explosive event known as a nova, in which the accumulated material detonates in a burst of energy. These novae are one of the most dramatic phenomena associated with white dwarf pulsars and provide a powerful tool for studying the behavior of matter under extreme conditions. As we continue to explore the dynamics of accretion in white dwarf pulsars, it is becoming clear that these objects may be crucial for understanding the broader processes that shape galaxies and star systems. The material that is accreted by a white dwarf pulsar can have a profound effect on the surrounding environment, especially in terms of the distribution of gas and dust. As the pulsar expels energy into the surrounding space, it can trigger the formation of new stars, initiate the collapse of gas clouds, and influence the overall evolution of the galaxy. This makes white dwarf pulsars not only fascinating objects in their own right, but also important players in the cosmic cycle of star formation and galactic evolution. Moreover, the study of white dwarf pulsars also intersects with the growing field of gravitational wave astronomy. As previously mentioned, gravitational waves are ripples in spacetime caused by the acceleration of massive objects. While much of the focus in gravitational wave research has been on the mergers of black holes and neutron stars, white dwarf pulsars and binary systems are also expected to produce detectable gravitational waves. The detection of these waves could provide a new avenue for studying the properties of white dwarf pulsars, including their masses, spins, and the way they interact with their companion stars. To date, gravitational waves from white dwarf pulsars have not been observed directly, but the potential for such detections is a tantalizing prospect. With the rapid advancements in gravitational wave detectors like LIGO and Virgo, it's possible that in the near future, we could detect the faint signals produced by these pulsars and gain new insights into their behavior. This could allow us to study the interior structure of white dwarfs, probe the nature of the spacetime around them, and even test our theories of gravity in ways that were previously impossible. The future of white dwarf pulsar research is bright, with many exciting possibilities on the horizon. The combination of advanced observational tools, such as space-based telescopes and gravitational wave detectors, along with improved computational models and simulations, will enable us to probe deeper into the mysteries of these objects than ever before. As we learn more about the magnetic fields, accretion processes, and gravitational interactions of white dwarf pulsars, we will continue to unlock the secrets of the universe and expand our understanding of the fundamental forces that shape the cosmos. In the coming years, it's likely that we will uncover even more surprising and unexpected aspects of white dwarf pulsars. These objects may hold the key to solving some of the most profound mysteries in astrophysics, from the nature of dark matter and dark energy to the very structure of space-time itself. By continuing to study these enigmatic objects, we will not only expand our knowledge of the universe but also gain a deeper appreciation for the intricate and interconnected processes that govern the behavior of stars, galaxies, and the cosmos as a whole. It's important to remember that these objects, though small in size compared to other cosmic giants, represent the cutting edge of our understanding of the universe. They serve as a reminder that even the most seemingly ordinary stars can harbor extraordinary properties and behaviors that challenge our very understanding of the laws of physics. The study of white dwarf pulsars is an ongoing journey, one that will continue to provide us with new insights into the most fundamental questions about the nature of matter, energy, and the fabric of space-time. The search for answers to the mysteries of white dwarf pulsars is far from over. In fact, the more we learn about them, the more complex and intriguing they become. As we uncover the secrets of their magnetic fields, accretion processes, and interactions with binary companions, we continue to push the boundaries of what we know about the universe. There's still much to explore, and white dwarf pulsars offer an exciting frontier in modern astrophysics. One aspect of white dwarf pulsars that has captured the attention of astronomers is the potential for these objects to play a role in the creation of exotic, ultra-dense forms of matter. As mentioned earlier, the conditions inside white dwarfs are extreme. These stars are composed mainly of degenerate matter, a state of matter that occurs under intense pressure, where electrons are packed into the smallest possible space. When a white dwarf pulsar is part of a binary system and is accreting material from a companion star, the accretion process can significantly alter the conditions within the white dwarf. In some cases, the accretion of matter can lead to the formation of a massive explosion known as a nova, but it can also result in the creation of even more exotic forms of matter. For instance, as material builds up on the surface of the white dwarf, the pressure increases to the point where it could potentially cause the electrons in the matter to behave in ways that are not fully understood. In extreme cases, it's possible that the matter could enter a regime known as quark-gluon plasma, where quarks and gluons, fundamental particles that make up protons and neutrons, are freed from their usual confinement within these larger particles. This state of matter is thought to have existed just moments after the Big Bang and is one of the most mysterious and exciting areas of modern physics. Quark-gluon plasma is an exotic state of matter that scientists are eager to study in the laboratory, and white dwarf pulsars may provide a natural setting to study its behavior. However, this process is not fully understood yet, and much of the current research is theoretical. The question remains, could white dwarf pulsars be one of the cosmic laboratories where quark-gluon plasma forms? And if so, what can we learn from these extreme environments? The magnetic fields of white dwarf pulsars also hold immense scientific potential. The strength of these fields is far beyond what we encounter in most other astronomical objects, and they can have profound effects on the particles that orbit or interact with the pulsar. These magnetic fields can accelerate particles to incredibly high energies, creating powerful jets of radiation that can be detected across vast distances. Understanding the nature of these magnetic fields and how they interact with surrounding matter could lead to breakthroughs in our understanding of both astrophysical phenomena and fundamental physics. Another intriguing aspect of white dwarf pulsars is their potential to serve as natural laboratories for testing theories of relativity and quantum mechanics. These objects are located in environments where the effects of both general relativity, which governs the behavior of large-scale structures like stars and planets, and quantum mechanics, which governs the behavior of particles at the smallest scales, come into play. The extreme conditions within and around white dwarf pulsars, particularly in binary systems where they are accreting material, offer a unique opportunity to study the intersection of these two areas of physics in ways that are not possible with more familiar objects. In particular, the strong gravitational fields around white dwarf pulsars could allow us to test Einstein's theory of general relativity in extreme conditions. This theory has been tested in a variety of contexts, but there are still unanswered questions about how gravity behaves under such intense conditions. For instance, how do the magnetic fields of white dwarf pulsars interact with their gravitational fields? Could this reveal any discrepancies between predicted and observed gravitational effects? Future observations, particularly those involving gravitational wave astronomy, may provide the answers to these questions and help refine our understanding of gravity in extreme environments. Similarly, the quantum mechanical properties of white dwarf pulsars also provide an interesting avenue for research. In particular, the extreme pressures and densities inside these objects could cause quantum effects to become much more pronounced, possibly leading to the formation of exotic particles or behaviors that are not seen in less extreme environments. For instance, the conditions inside a white dwarf pulsar could potentially cause the emergence of new states of matter or new types of particle interactions that we are only just beginning to explore. As the field of astrophysics continues to advance, so too does our ability to observe and understand the behavior of white dwarf pulsars. In recent years, the advent of more sophisticated telescopes and observatories has allowed scientists to gather more detailed data about these objects than ever before. Space-based telescopes, in particular, offer a unique advantage when it comes to studying objects like white dwarf pulsars, as they can observe these stars across a wide range of wavelengths, from radio waves to X-rays. This enables scientists to build a more complete picture of the pulsar's structure, behavior, and the forces at play within its magnetic and accretion disks. One of the most promising tools in the study of white dwarf pulsars is the upcoming generation of gravitational wave detectors. While current detectors like LIGO and Virgo have already revolutionized our understanding of gravitational waves and have allowed us to observe the mergers of black holes and neutron stars, future detectors are expected to provide even more detailed observations of these cosmic phenomena. These detectors will be able to pick up the faint gravitational waves emitted by white dwarf pulsars, offering new ways to probe their properties and behavior. In addition, the study of white dwarf pulsars is likely to benefit from advancements in computational models and simulations. As our understanding of the physics involved in these objects grows, researchers will be able to refine their models to account for more variables and provide more accurate predictions about their behavior. These models will be crucial for interpreting the data collected by telescopes and gravitational wave detectors and for answering the many questions that remain about these fascinating cosmic objects. White dwarf pulsars are among the most intriguing and enigmatic objects in the universe. These stellar remnants, with their unique combination of magnetic fields, radiation, and accretion processes, hold the potential to reveal new insights into the fundamental workings of the universe. From the creation of exotic matter to the testing of theories of relativity and quantum mechanics, the study of white dwarf pulsars is a rapidly evolving field that promises to expand our understanding of the cosmos in ways that we can only begin to imagine. While much has already been learned about these objects, the true extent of their mysteries is still unfolding. As our technology advances and our theoretical models continue to evolve, the next few decades of research into white dwarf pulsars are likely to yield some of the most exciting discoveries in modern astrophysics. For now, these fascinating objects remain a symbol of the limitless curiosity and the relentless pursuit of knowledge that drives scientific discovery. Each new observation, each new theoretical breakthrough, brings us one step closer to unlocking the secrets of the universe and understanding the forces that shape our cosmos. As we continue to delve into the mysteries of white dwarf pulsars, one of the most compelling aspects is their potential to serve as cosmic laboratories for understanding the universe's most fundamental forces. Unlike other astrophysical objects, white dwarf pulsars provide a unique combination of extreme conditions, such as intense magnetic fields, dense matter, and rapid rotation, all of which can offer insights into physics at its most basic level. One intriguing area of study is the role that white dwarf pulsars could play in our understanding of the fundamental forces in nature, specifically the force of magnetism. In most stars, magnetic fields are relatively weak compared to the overall mass of the star. However, in white dwarf pulsars, the magnetic fields are so strong that they fundamentally alter the way particles move within the star. The effect of these magnetic fields on matter, radiation, and even light itself can provide crucial clues about how magnetic forces behave in the most extreme environments. For instance, these magnetic fields can have a significant impact on the motion of charged particles near the pulsar. When matter from a companion star is accreted onto a white dwarf, the intense magnetic field can accelerate these particles to nearly the speed of light. This process, known as magnetospheric acceleration, can lead to the creation of highly energetic radiation, including X-rays and gamma rays, which can be observed by telescopes on Earth. By studying this radiation, scientists can learn more about the strength and behavior of magnetic fields in these extreme environments. Additionally, the rapid rotation of white dwarf pulsars adds another layer of complexity to our understanding of their magnetic fields. As the pulsar spins, the magnetic field lines are twisted and distorted, which can lead to the creation of powerful electromagnetic waves. These waves can travel outward from the pulsar, carrying information about the internal structure and dynamics of the star. By studying the way these electromagnetic waves interact with the surrounding matter, astronomers can gain a deeper understanding of how magnetic fields shape the behavior of matter at the most fundamental levels. Another aspect of white dwarf pulsars that has significant implications for our understanding of astrophysics is their role in the formation of heavy elements. When a white dwarf pulsar is part of a binary system and is accreting material from a companion star, the intense pressure and temperature within the pulsar can lead to the creation of heavy elements such as iron and nickel. These elements are then expelled into the surrounding space, enriching the interstellar medium with the building blocks for future stars, planets, and even life. The process by which heavy elements are created in white dwarf pulsars is similar to that in other stellar remnants, such as neutron stars and supernovae. However, the unique properties of white dwarf pulsars, such as their smaller size, higher density, and magnetic fields, make them particularly interesting objects for studying the mechanisms behind the creation of these elements. The study of these elements not only helps us understand the life cycle of stars but also provides insights into the processes that govern the evolution of galaxies and the formation of planetary systems. White dwarf pulsars could also play a crucial role in the study of cosmic distances and the expansion of the universe. Since these objects emit radiation across a wide range of wavelengths, they can be used as cosmic beacons to measure the distance to far-off galaxies. By studying the pulsations of white dwarf pulsars in distant galaxies, astronomers can gain a more accurate understanding of the scale of the universe and refine their measurements of the rate at which the universe is expanding. This, in turn, has significant implications for our understanding of the origins and future of the cosmos. The study of white dwarf pulsars also intersects with one of the most profound questions in modern science: the search for extraterrestrial life. While the harsh environments around white dwarf pulsars would seem inhospitable to life as we know it, these objects still hold potential for shedding light on the conditions that might support life elsewhere in the universe. For example, the study of how planets and moons interact with white dwarf pulsars could provide clues about how life might survive in extreme environments, such as those found on exoplanets orbiting other stars. In particular, the interaction between the pulsar's radiation and the surrounding material could have profound effects on the habitability of nearby planets. The high-energy radiation emitted by white dwarf pulsars could strip away the atmospheres of any planets within a certain distance, making it difficult for life to take hold. However, some researchers believe that the intense radiation could also create conditions that are conducive to the development of life. This is because radiation could trigger chemical reactions that form the basic building blocks of life, similar to how cosmic rays are thought to have played a role in the origins of life on Earth. As we continue to explore the potential habitability of planets around white dwarf pulsars, we are also deepening our understanding of how life might arise and survive in environments that are vastly different from Earth. In this sense, white dwarf pulsars could offer us a unique perspective on the conditions necessary for life in the cosmos, allowing us to expand our search for extraterrestrial life beyond the familiar confines of the habitable zone around main sequence stars. Moreover, the study of white dwarf pulsars has far-reaching implications for our understanding of the ultimate fate of the universe. These objects, along with other stellar remnants such as neutron stars and black holes, provide critical insights into the life cycle of stars and the end stages of stellar evolution. By studying the behavior of white dwarf pulsars and their interactions with surrounding matter, we can gain a better understanding of how the universe will evolve in the distant future. In particular, white dwarf pulsars are thought to represent a key stage in the life of stars with low to medium masses. These stars, which make up the majority of the stars in the Milky Way, will eventually burn out and evolve into white dwarfs. Over the course of billions of years, these white dwarfs will cool and fade, eventually becoming cold, dark remnants known as black dwarfs. While the timescales involved in this process are much longer than human lifetimes, the study of white dwarf pulsars gives us a glimpse into the distant future of our own sun and the fate of all stars like it. The future of white dwarf pulsar research looks promising, with new telescopes and observational techniques allowing astronomers to gather more data than ever before. One of the most exciting prospects is the upcoming launch of the James Webb Space Telescope, which is set to revolutionize our understanding of the universe. This powerful telescope will be able to observe the most distant white dwarf pulsars and study their behavior in unprecedented detail, offering new insights into their structure, composition, and magnetic fields. In addition, the development of more advanced ground-based telescopes, such as the Extremely Large Telescope, ELT, in Chile, will enable scientists to study the most faint and distant white dwarf pulsars in the universe. These telescopes will allow astronomers to observe the pulsars at higher resolutions and across a broader range of wavelengths, providing more detailed and accurate data than ever before. The combination of these new observational tools, along with advances in computational modeling and simulation, will undoubtedly lead to many exciting discoveries in the coming years. As we continue to unlock the secrets of white dwarf pulsars, we can expect to gain a deeper understanding of the fundamental forces that govern the universe, the nature of exotic forms of matter, and the ultimate fate of stars and galaxies. White dwarf pulsars, with their unique combination of features, will remain a fascinating area of study for astronomers and astrophysicists for many years to come, offering new opportunities to explore the most profound questions in science. As we continue to explore the intricacies of white dwarf pulsars, another captivating aspect to consider is the role of these objects in the broader context of stellar evolution. While we've discussed their fascinating characteristics as isolated entities, their interactions with companion stars and binary systems also offer a treasure trove of knowledge about stellar dynamics. These interactions, in fact, are some of the most crucial aspects that lead to the formation of white dwarf pulsars in the first place. In binary star systems, a white dwarf can be paired with a companion star, often a more massive star in its later stages of evolution. The transfer of material from the companion star to the white dwarf can trigger a series of events that eventually leads to the pulsating behavior. This process, known as accretion, involves the white dwarf drawing in matter from its companion. As this material spirals in toward the white dwarf, it forms an accretion disk. The intense gravitational and magnetic fields around the white dwarf accelerate the matter to extremely high velocities, generating significant amounts of energy in the form of light and radiation. It is in these scenarios that the magnetic fields of the white dwarf pulsar can come into play most dramatically. When the material from the companion star interacts with the white dwarf's magnetic field, the result can be an even more powerful release of radiation. This radiation can be emitted as X-rays, gamma rays, and even radio waves, depending on the energy levels involved. The pulsations that we observe in these stars are often linked to the periodic release of energy caused by the rotation of the white dwarf and the behavior of its magnetic field. These pulses are not just intriguing phenomena but also act as cosmic beacons, allowing astronomers to measure the rotation rates, magnetic field strength, and other properties of these objects. The intense interaction between the white dwarf pulsar and its companion star in such systems can also lead to significant changes in the characteristics of the companion star. For example, the material being pulled from the companion star can cause it to lose mass over time. This process, known as mass transfer, can lead to the eventual death of the companion star, transforming it into a red giant, or even contributing to the formation of a second white dwarf or a neutron star, depending on the mass and final evolution of the companion. But what happens when the material accreted by the white dwarf pulsar reaches a critical threshold? This question leads us to one of the most fascinating aspects of these stars: the potential for a nova or even a type Ia supernova. When the white dwarf accumulates enough material, the pressure and temperature at its core can rise to the point where nuclear fusion reignites. This can result in an explosive outburst of energy, known as a nova, which temporarily increases the star's brightness. While a nova may seem like a brief, temporary phenomenon, it is part of the ongoing process of stellar evolution, providing astronomers with valuable clues about the nature of these distant objects. However, in some cases, the continued accretion of mass onto the white dwarf can lead to a more cataclysmic event, a type Ia supernova. In this scenario, the white dwarf reaches a critical mass known as the Chandrasekhar limit, typically around 1.4 times the mass of our Sun. Once this threshold is crossed, the white dwarf undergoes a rapid and uncontrollable collapse, triggering a thermonuclear explosion that can outshine an entire galaxy for a brief period of time. These supernovae are not only spectacular cosmic events but are also crucial for understanding the synthesis of heavy elements, as they produce vast amounts of iron, nickel, and other heavy elements, which are then scattered across the universe. While the accretion process is a key element in the life cycle of a white dwarf pulsar, it is also essential to examine the inherent challenges involved in observing these fascinating objects. White dwarf pulsars, by their very nature, are often difficult to detect. The combination of their small size and the intense radiation that they emit in bursts or pulses means that they can be easily obscured by other cosmic objects. To overcome this, astronomers rely on highly sensitive instruments capable of detecting specific wavelengths of radiation, such as X-rays or radio waves, that these pulsars emit. One of the most important tools for studying white dwarf pulsars is the use of space-based telescopes. Instruments like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton provide the high-resolution imaging and spectroscopic capabilities necessary to observe the high-energy radiation emitted by these objects. Additionally, radio telescopes, such as the Arecibo Observatory, which, before its collapse in 2020, played a pivotal role in pulsar studies, are instrumental in detecting the periodic radio waves emitted by pulsars. These telescopes, however, have their limits, and much of the research on white dwarf pulsars relies on a combination of observational techniques. As new technologies continue to be developed, astronomers are gaining the ability to study these objects in greater detail than ever before. The upcoming launch of the James Webb Space Telescope, for example, will provide unprecedented infrared capabilities, allowing scientists to probe deeper into the environments around white dwarf pulsars and gain a better understanding of their formation and behavior. The continued development of ground-based observatories is also contributing to the growing body of knowledge about white dwarf pulsars. The construction of massive new telescopes, such as the Extremely Large Telescope, ELT, in Chile, will significantly enhance our ability to study distant white dwarf pulsars with greater precision. These telescopes will allow astronomers to study the pulsing behavior of white dwarf pulsars in real time, providing insights into the physics of matter under extreme conditions. Beyond the technical advancements, one of the most profound aspects of studying white dwarf pulsars is how they help us understand the life cycle of stars. These compact remnants of stars represent the final evolutionary stage of low to medium mass stars, providing a fascinating window into the ultimate fate of our Sun. Over billions of years, as our own Sun exhausts its nuclear fuel, it will shed its outer layers, leaving behind a dense, hot core, what we would recognize as a white dwarf. Understanding the behavior of white dwarf pulsars allows us to better predict the future of our solar system and the fate of Earth itself. Furthermore, these stars are not just relevant for understanding stellar evolution, they also play a crucial role in our understanding of the fundamental laws of physics. The extreme conditions present in white dwarf pulsars, including intense gravitational fields, strong magnetic fields, and high temperatures, offer a natural laboratory for studying the behavior of matter under extreme conditions that can't be replicated on Earth. This makes white dwarf pulsars not only important objects for astronomy but also for the broader fields of theoretical physics and cosmology. One intriguing possibility is the study of quantum effects in the dense interiors of white dwarf pulsars. In these environments, matter is compressed to such high densities that quantum mechanics becomes a dominant factor in governing the behavior of particles. This opens up the possibility for new insights into the strange and fascinating world of quantum gravity, a field that seeks to unify quantum mechanics and general relativity, two of the most successful but seemingly incompatible theories in modern physics. By studying the properties of white dwarf pulsars and their magnetic fields, researchers may be able to uncover new details about how quantum mechanics works in the presence of extremely strong gravitational forces. White dwarf pulsars also offer a window into the future of cosmology. As we learn more about how these stars evolve and interact with their environments, we gain new insights into the overall structure and dynamics of galaxies. White dwarf pulsars are often found in the remnants of star clusters and other stellar populations, providing valuable clues about the history of star formation and galactic evolution. Their study, therefore, is not just an exploration of individual stars but also a key piece in the puzzle of how galaxies, including our own Milky Way, have evolved over cosmic time. The study of white dwarf pulsars is not just about understanding a unique class of astronomical objects. It is about unlocking the secrets of the universe itself. From the extreme magnetic fields and rapid rotations of these stars to their role in the life cycle of stars and the creation of heavy elements, white dwarf pulsars offer a unique opportunity to explore the most fundamental questions in astrophysics. Their study provides essential insights into stellar evolution, the nature of matter, and the fundamental forces that govern the cosmos. As our ability to observe and understand these objects continues to improve, the mysteries of white dwarf pulsars will undoubtedly reveal even more profound secrets about the universe we live in. White dwarf pulsars, through their enigmatic characteristics, continue to captivate astronomers and physicists alike. With every new discovery about their magnetic fields, accretion processes, and interactions with their surroundings, we push the boundaries of what we know about the universe. Their role as cosmic laboratories allows us to test fundamental theories of physics, such as general relativity, electromagnetism, and quantum mechanics, in environments that are simply impossible to replicate on Earth. One of the most fascinating aspects of white dwarf pulsars is their ability to reveal more about the nature of exotic matter. While most of the matter we encounter in our daily lives is composed of atoms, white dwarf pulsars exist in a realm where traditional matter is pushed to its limits. In these dense stellar remnants, atoms are compressed so tightly that the electrons are forced to occupy the same quantum states, creating what's known as degenerate matter. This form of matter is unlike anything we experience on Earth, and it provides important clues about the behavior of particles under extreme pressures. In fact, white dwarf pulsars are perfect examples of the intricate balance between gravity and quantum mechanics. The intense gravitational pressure from the white dwarf's compact mass pulls the atoms together, while quantum mechanical principles, such as the Pauli exclusion principle, prevent the particles from collapsing any further. This delicate equilibrium results in a star that is incredibly dense, about the mass of the Sun packed into a volume roughly the size of Earth. By studying these stars, astronomers gain insights into how matter behaves under these extreme conditions, helping us understand phenomena like neutron stars and black holes, which take this process even further to the extreme. As we look to the future, the study of white dwarf pulsars may also play a key role in expanding our knowledge of gravitational waves. These ripples in spacetime, first predicted by Albert Einstein and detected by LIGO, Laser Interferometer Gravitational Wave Observatory, in 2015, provide a new way of observing the universe. Gravitational waves are created by the acceleration of massive objects, such as the merging of black holes or neutron stars, but it is possible that white dwarf pulsars could also contribute to these signals, especially in binary systems where the pulsar interacts with another massive object. As gravitational wave astronomy advances, it could offer new insights into the life cycle of white dwarf pulsars, potentially allowing us to observe phenomena that were previously undetectable. Another key area of research is the role of white dwarf pulsars in the broader context of cosmic recycling. These pulsars are essential players in the distribution of heavy elements throughout the universe. As mentioned earlier, when a white dwarf reaches the Chandrasekhar limit and undergoes a thermonuclear explosion, the resulting supernova ejects vast amounts of material into the surrounding space. This material includes not only iron and nickel but also other elements like carbon, oxygen, and even heavier elements that are vital for the formation of planets and life itself. The explosion of a white dwarf pulsar in a Type I supernova, for instance, can create enough energy to produce elements that are even heavier than iron, including elements like gold, platinum, and uranium. These elements are then scattered across the universe, eventually becoming part of new stars, planets, and other celestial bodies. In this way, white dwarf pulsars contribute to the process of galactic enrichment, which is crucial for the ongoing cycle of star and planet formation. By understanding how these elements are created and distributed, astronomers are able to piece together the complex story of the universe's evolution. Moreover, as we consider the future of the universe, white dwarf pulsars provide important clues about its fate. These stellar remnants are often the last survivors of their stellar systems, and their slow, gradual cooling over billions of years offers a glimpse into the long-term future of stars like our Sun. As our own Sun eventually reaches the end of its life, it will shed its outer layers, leaving behind a white dwarf that will slowly cool and fade over trillions of years. This process, which can take far longer than the current age of the universe, raises fascinating questions about the ultimate fate of stars and their remnants. While white dwarf pulsars are primarily studied in the context of individual objects, they also offer a broader perspective on the life cycle of stars in general. These pulsars are the remnants of stars that were once similar to our Sun, and their evolution reflects the ultimate fate of solar-type stars. Understanding the processes that lead to the formation of white dwarf pulsars and other stellar remnants allows us to predict the long-term evolution of our own Sun and the Earth. This knowledge is crucial for understanding the distant future of our solar system and the eventual fate of our planet. The fascinating nature of white dwarf pulsars also leads to important questions about the possibilities of life in the universe. While these stars themselves are inhospitable to life, the heavy elements they produce and disperse are essential for the formation of planets. In fact, the process of star death and rebirth, facilitated in part by the explosive demise of white dwarf pulsars, is thought to play a crucial role in the formation of life-supporting planets. This cosmic cycle of creation and destruction provides the building blocks for life as we know it, making the study of white dwarf pulsars an integral part of understanding the origins and evolution of life in the universe. White dwarf pulsars are much more than just strange, exotic objects in the sky. They represent the final stages of stellar evolution for low to medium mass stars and serve as powerful tools for exploring the fundamental forces and processes that govern the universe. Whether through their role in testing quantum mechanics and general relativity, their contributions to the synthesis and distribution of heavy elements, or their potential to help us understand the future of our own solar system, white dwarf pulsars offer a wealth of knowledge about the universe. As our observational tools improve and our understanding of these enigmatic stars deepens, we will continue to unlock the secrets of these fascinating objects, gaining a better understanding of the universe's past, present, and future. While neutron stars are far denser and black holes represent the ultimate collapse of matter, white dwarf pulsars show that even within less extreme densities, nature can produce some of the most exotic behaviors in the universe. These objects demonstrate that powerful magnetic fields and rapid rotation can manifest without the need for a neutron star's crushing gravity. Instead, they reveal that even a star made of degenerate matter, electrons squeezed into quantum states, can generate beams of electromagnetic radiation and behave as cosmic lighthouses. The evolutionary pathways leading to the formation of white dwarf pulsars are deeply intertwined with binary star systems. Typically, a star with an initial mass similar to or slightly higher than the Sun exhausts its nuclear fuel, expands into a red giant, and eventually sheds its outer layers. What remains is the white dwarf core. However, if this white dwarf has a companion star, and conditions are right, the gravitational interplay between the two can lead to the accumulation of material onto the white dwarf's surface. The accreted material can not only increase the white dwarf's mass but also spin it up, dramatically increasing its rotational speed. Over time, the accumulation of angular momentum can transform a slow-rotating white dwarf into a rapid spinner, setting the stage for pulsar-like behavior. If the white dwarf already possesses a strong magnetic field, or if accretion processes amplify its magnetic field, the conditions become ideal for the emergence of pulsar-like emissions. The white dwarf's magnetic poles, slightly misaligned with its rotational axis, act as the source of radiation beams. As the star spins, these beams sweep through space, producing the pulsating signals that we observe from Earth. What makes white dwarf pulsars particularly intriguing is the range of timescales and energies involved. Their rotational periods are generally slower than those of neutron star pulsars, sometimes on the order of seconds to minutes, compared to the milliseconds seen in their denser cousins. Nevertheless, the energies involved are still immense, owing to the combination of rotational inertia and magnetic field strength. In fact, in some cases, the rotational energy loss rates of white dwarf pulsars rival those of certain neutron stars, challenging long-held assumptions about how energy is dissipated in compact objects. The discovery of AR Scorpii, the first confirmed white dwarf pulsar, opened an entirely new chapter in astrophysics. Prior to its identification, the notion that a white dwarf could emit pulsar-like radiation seemed highly speculative. Yet observations of AR Scorpii showed clear evidence of highly regular pulses of optical and radio emissions, synchronized with the rotation of the white dwarf. Moreover, these pulses exhibited variability tied to the binary orbit, suggesting that interactions with the companion star played a crucial role in shaping the observed behavior. The magnetic interactions between the white dwarf and its companion star create an environment rich in charged particles and magnetic reconnections. These dynamic processes accelerate electrons to relativistic speeds, causing them to emit synchrotron radiation, the hallmark of pulsar-like emissions. The beams emitted by AR Scorpii are thought to arise from this synchrotron mechanism, modulated by the rotation and magnetic field configuration of the white dwarf. As researchers continue to study systems like AR Scorpii, they are uncovering a surprising diversity among white dwarf pulsars. Not all white dwarf pulsars are created equal. Some may exhibit stronger magnetic fields, faster rotations, or more violent interactions with their companions. These variations provide crucial data points for refining theoretical models and expanding our understanding of how pulsar mechanisms operate across different types of stellar remnants. The presence of strong magnetic fields in white dwarf pulsars also raises fundamental questions about the origin and evolution of magnetic fields in stars. How do some stars retain or amplify their magnetic fields during the transition from main sequence star to white dwarf? Is it possible that dynamo mechanisms, similar to those that generate Earth's magnetic field, operate within the dense interiors of these remnants? Or do fossil magnetic fields, inherited from earlier stages of stellar evolution, simply persist and become intensified as the star contracts? Answering these questions requires a multidisciplinary approach, combining observations across the electromagnetic spectrum with sophisticated theoretical modeling and computer simulations. Radio telescopes like the Very Large Array, optical observatories like the Hubble Space Telescope, and future X-ray missions will all play critical roles in uncovering the secrets of white dwarf pulsars. Meanwhile, advancements in computational astrophysics are enabling researchers to simulate the complex magnetohydrodynamic processes occurring within and around these stars, offering new insights into the life cycles of magnetic fields in the cosmos. Another exciting avenue of research involves the potential connection between white dwarf pulsars and gravitational waves. While neutron star mergers have already been detected as sources of gravitational waves, some scientists speculate that certain interactions involving white dwarf pulsars, especially in tight binary systems, could produce detectable ripples in spacetime. Although the gravitational wave signals from white dwarf binaries would be weaker than those from neutron star collisions, they fall within the detection range of proposed space-based observatories like the Laser Interferometer Space Antenna, LISA. If gravitational waves from white dwarf binaries are detected, it would provide a completely new way to study these enigmatic objects. Unlike electromagnetic radiation, Gravitational waves carry information about the motion and mass distribution of objects without being scattered or absorbed by intervening matter. Thus, gravitational wave observations could offer an unobstructed view into the inner workings of white dwarf pulsar systems, complementing traditional astronomical techniques and revealing hidden aspects of their behavior. Beyond their role in gravitational wave astronomy, white dwarf pulsars may also be crucial in understanding the chemical evolution of galaxies. The processes that create and destroy white dwarf pulsars involve the fusion of heavier elements and the dispersal of enriched material into interstellar space. Through nova outbursts, where accumulated hydrogen on a white dwarf's surface ignites in a thermonuclear explosion, these stars contribute to the enrichment of the interstellar medium with elements like carbon, nitrogen, and oxygen. Thus, white dwarf pulsars are not merely cosmic curiosities. They are active participants in the grand cycle of stellar birth, death, and rebirth. The broader implications of studying white dwarf pulsars extend even to the search for extraterrestrial life. Understanding how magnetic fields, radiation, and stellar winds from exotic objects like white dwarf pulsars affect nearby planetary systems could inform models of habitability around other stars. In systems where a planet orbits a white dwarf pulsar, the intense radiation and magnetic fields might either sterilize the planet's surface or, under certain conditions, drive complex chemical reactions that could give rise to life. As we continue to unlock the mysteries of white dwarf pulsars, it becomes increasingly clear that they occupy a pivotal place in our cosmic story. They challenge our preconceptions about how stars live and die, reveal new facets of fundamental physics, and offer tantalizing glimpses into the hidden processes that shape galaxies and, by extension, the universe itself. With each new discovery, white dwarf pulsars remind us that even in death, stars can blaze forth with unexpected and awe-inspiring vigor, illuminating the cosmos in ways we are only just beginning to understand. These emissions arise because the intense magnetic field funnels charged particles along its lines, accelerating them to relativistic speeds. As these particles spiral along the magnetic field, they emit radiation that can be detected across a broad range of the electromagnetic spectrum, including radio waves, X-rays, and even gamma rays. The combination of rapid rotation and a tilted magnetic axis causes the beams of radiation to sweep across space, just like the beams of a lighthouse, leading to the pulse signals that astronomers observe. This pulsar-like activity from white dwarfs challenges long-standing assumptions about the exclusivity of neutron stars in producing such phenomena. For decades, pulsar behavior was thought to be a signature trait unique to neutron stars because of their extreme magnetic fields and rapid spins. However, the discovery of white dwarf pulsars proved that the fundamental ingredients needed to create pulsar emissions, strong magnetism, fast rotation, and an environment rich in charged particles, can exist under less extreme conditions than previously believed. One particularly famous white dwarf pulsar, AR Scorpii, has provided a wealth of observational data that supports this understanding. This binary system, consisting of a white dwarf and a red dwarf companion, exhibits powerful, coherent radio and optical pulsations every 1.97 minutes. The precision and consistency of these pulses closely mimic the behavior of classic neutron star pulsars, yet arise from a system with a white dwarf at its heart. AR Scorpii's discovery was groundbreaking because it offered the first clear-cut evidence of a white dwarf behaving unmistakably like a pulsar. In studying AR Scorpii, astronomers realized that the white dwarf's magnetic field was interacting with the red dwarf companion in an electrifying way. As the white dwarf spins, its magnetic field sweeps through the outer layers of the red dwarf, accelerating electrons and creating a dense cloud of relativistic particles. These particles, trapped within the intense magnetic field, emit synchrotron radiation, a telltale sign of high-energy astrophysical processes. Even more fascinating is the idea that white dwarf pulsars may actually be relatively common in the galaxy, but hard to detect due to their typically lower energy outputs compared to neutron star pulsars. Their emissions, often spanning radio and optical wavelengths rather than solely X-ray or gamma ray, make them less conspicuous to telescopes designed to hunt for the high-energy signatures of traditional pulsars. This suggests that with more targeted observational strategies, astronomers might uncover many more white dwarf pulsars lurking in binary systems across the Milky Way. The potential abundance of white dwarf pulsars raises important questions about stellar life cycles. If white dwarf pulsars are a natural endpoint for many binary systems, it could imply that the end states of stars are even more varied than current models predict. Instead of simply becoming a cold, inert white dwarf or exploding in a supernova, some stars might undergo a transitional phase where they shine once more, not with nuclear fusion, but with the sheer kinetic and magnetic energy of their rotation. Moreover, the study of white dwarf pulsars offers profound insights into magnetic field evolution. It's not entirely clear how some white dwarfs retain, or even amplify their magnetic fields after formation. While some theories suggest that magnetic fields are fossil remnants from the progenitor stars, others propose that binary interactions, accretion processes, or internal dynamo effects within the white dwarf itself could lead to magnetic field amplification. Observations of white dwarf pulsars provide critical data points that could help resolve this debate. Another tantalizing possibility that arises from white dwarf pulsar research is the idea that these objects might serve as progenitors for certain types of supernovae, particularly type I supernovae. In some scenarios, a white dwarf in a binary system continues to accrete matter until it approaches the Chandrasekhar limit, about 1.4 times the mass of the Sun. At this point, the white dwarf becomes unstable and undergoes a catastrophic thermonuclear explosion. However, if a white dwarf has been spun up significantly by accretion, it could temporarily resist collapse by centrifugal forces, allowing it to exceed the Chandrasekhar limit before exploding. Such spin-boosted white dwarfs could produce supernovae with unusual properties, potentially explaining some of the peculiar and diverse supernova events observed in distant galaxies. If white dwarf pulsars are indeed precursors to certain supernovae, studying them could provide the missing link needed to understand the mechanisms behind these cosmic explosions. The exploration of white dwarf pulsars doesn't stop at their astrophysical implications. Their study also intersects with the quest to detect gravitational waves, ripples in spacetime predicted by Einstein's theory of general relativity. While massive black hole mergers have already been detected via gravitational waves, compact binaries involving white dwarfs are thought to be a major source of low-frequency gravitational waves, which future space-based detectors like LISA, the Laser Interferometer Space Antenna, aim to observe. In particular, tight binary systems containing a white dwarf pulsar could produce a steady hum of gravitational waves that, when detected, would open an entirely new window into the dynamics of compact stellar remnants. Observing these signals could not only confirm theoretical predictions but also reveal hidden populations of white dwarf pulsars and deepen our understanding of the end stages of stellar evolution. Beyond astrophysics, white dwarf pulsars touch on fundamental questions about the nature of matter, energy, and the universe itself. They remind us that the cosmos is far from a static or uniform place. It is dynamic, evolving, and filled with surprises that challenge our models and force us to rethink basic assumptions. Every pulse from a white dwarf pulsar is a whisper from a distant, ancient star, telling us stories about its past, about the violence and beauty of cosmic evolution, and about the universal forces that shape everything we see. Even as we expand our catalog of known white dwarf pulsars, countless mysteries remain. How common are they truly? What determines whether a white dwarf becomes a pulsar? How exactly do their magnetic fields evolve over millions or even billions of years? And could white dwarf pulsars represent just one phase in an even more complex life cycle involving transformations into neutron stars under certain extreme conditions? The quest to answer these questions is ongoing, and with every observation, we edge closer to a fuller, richer understanding of the universe. In the dance of stars, in the whisper of magnetic fields, and in the flashes of pulsed light crossing the void of space, white dwarf pulsars continue to challenge, inspire, and expand the horizons of human knowledge. Moreover, the study of systems like AR Scorpii has opened new avenues for probing the nature of magnetospheres around compact stars. In white dwarf pulsars, the magnetosphere, the region dominated by the star's magnetic field, is filled with energetic particles that can radiate across a vast range of wavelengths. Understanding how these magnetospheres evolve and interact with surrounding material allows scientists to model similar environments around other stellar remnants, providing deeper insights into astrophysical plasma behavior. The precision of white dwarf pulsar emissions also enables scientists to use them as cosmic laboratories for testing fundamental physics. For example, by studying the timing of the pulses and the way they vary over time, researchers can measure the effects of gravitational waves, study the behavior of matter under extreme electromagnetic forces, and even place constraints on theories that extend beyond general relativity. Each pulse acts like a cosmic clock, ticking away in a manner that can reveal subtle shifts in the surrounding space-time fabric. White dwarf pulsars also have the potential to inform us about the end stages of stellar and planetary system evolution. Many white dwarfs are known to host remnants of planetary systems, such as asteroid belts or even shattered planets. In some cases, the interaction between a white dwarf's magnetic field and debris from these destroyed worlds could produce observable emissions, adding yet another layer of complexity to the pulsar behavior. Thus, studying these systems could illuminate the fates of planetary systems, including our own, long after their host stars have died. Over time, as the white dwarf loses energy through radiation and particle emission, it is expected to gradually slow its spin. However, the timescales involved are immense, often spanning billions of years, meaning that a white dwarf pulsar could remain active for an extraordinary period, far beyond the lifespans of many other cosmic phenomena. The gradual deceleration of its rotation, combined with the eventual dissipation of its magnetic field, suggests that these pulsars may not last forever, but their life cycle could be vastly different from that of neutron star pulsars. The long-term evolution of white dwarf pulsars presents intriguing questions about the stability of their magnetospheres. As their rotational speed decreases and their magnetic fields weaken, the intensity of their emitted radiation will likely diminish, and they could eventually fade into obscurity. This process would mark the transition from an active pulsar state to a silent white dwarf, a seemingly paradoxical fate for an object that, at one point, pulsated with the energy of the cosmos. Yet even as these stars age and their energetic emissions fade, they leave behind an important legacy. The study of how white dwarf pulsars evolve could offer clues about the broader processes governing stellar evolution, including the recycling of material in star-forming regions. The eventual cooling of the white dwarf will cause it to become a black dwarf, a theoretical object that no longer emits any significant heat or light. While this stage lies far in the future, it underscores the transitory nature of all stellar remnants. The complexities of these pulsars also extend to the study of their progenitor systems. How do these stars form their magnetic fields, and what factors lead to the creation of such intense emissions? We still don't fully understand the intricate mechanics that allow white dwarf pulsars to maintain such strong and sustained magnetic fields. In some systems, particularly in binary white dwarf pulsars, the interaction between the two stars, whether through accretion of material or tidal interactions, could play a crucial role in strengthening the magnetic fields of one or both stars. This further complicates our understanding of their origin and evolution. In addition to their role in stellar evolution, white dwarf pulsars offer potential applications in a variety of fields, including gravitational wave astronomy. As previously mentioned, compact binaries containing white dwarf pulsars are expected to produce gravitational waves as their orbits decay over time. This radiation carries information about the internal structure of the stars involved, their masses, and the nature of the gravitational interactions at play. The detection of these gravitational waves could enhance our understanding of both general relativity and the behavior of matter in extremely dense environments. But white dwarf pulsars aren't just useful for astrophysical theories or the development of new technologies. Their discovery and study are also a testament to the unexpected nature of the universe. For a long time, we believed that the most extreme phenomena, such as the generation of pulsar-like emissions, could only occur in the presence of neutron stars, the densest and most compact objects known to exist. Yet white dwarf pulsars have shown us that there are always more secrets to uncover, often in places we least expect. This realization pushes the boundaries of what we thought we knew about the universe and invites astronomers to explore new areas of research. White dwarf pulsars are an essential part of this exploration. As our ability to detect faint cosmic signals improves, we may find even more examples of these rare and intriguing objects across the galaxy. Their study will not only expand our knowledge of stellar and binary system evolution, but it will also challenge our understanding of how stars live and die in ways we hadn't imagined before. As astronomers refine their observational techniques, the discovery of more white dwarf pulsars could offer a new era of astrophysical insights. Current observational instruments, such as space-based telescopes like the Hubble and the Chandra X-ray Observatory, combined with ground-based radio observatories like the Arecibo telescope, before its collapse, are already providing detailed data on these pulsar systems. The development of next-generation observatories, such as the James Webb Space Telescope, JWST, and the Square Kilometer Array, SKA, promises to vastly enhance our capacity to detect and analyze faint pulsations from distant white dwarf systems. These advancements could lead to breakthroughs in several areas. One exciting avenue of research is the study of gravitational lensing, where the intense gravitational fields around white dwarf pulsars may warp spacetime and distort the light from objects behind them. By analyzing the distortions in the light curves, astronomers can gain valuable insights into the precise mass, size, and density of the white dwarf, as well as the spacetime curvature in the region surrounding it. This would allow scientists to test general relativity in extreme conditions and observe phenomena that can't be reproduced on Earth. As our understanding of white dwarf pulsars deepens, we may also uncover more about their role in the formation of exotic objects. The process by which white dwarf pulsars interact with nearby material could lead to the creation of complex, exotic states of matter. For example, the accretion of gas from a companion star could potentially lead to the formation of a magnetar-like object, where the magnetic field is strong enough to cause intense bursts of gamma radiation. These interactions may also contribute to the formation of unusual cosmic phenomena like supernovae, or the merging of compact objects, which produce gravitational waves detectable by instruments like LIGO and Virgo. The extreme conditions surrounding white dwarf pulsars could provide us with unique insights into the very fabric of matter. As these stars spin faster and faster, their magnetic fields become increasingly powerful. The study of these magnetospheres offers the potential for understanding the behavior of matter and magnetic fields that are millions to billions of times stronger than anything we can replicate on Earth. This could lead to a new era in material science, particularly in the study of plasma physics and the behavior of charged particles in extreme electromagnetic environments. Furthermore, the interaction between white dwarf pulsars and their companion stars opens up fascinating questions about binary star evolution. In some systems, the gravitational pull of a white dwarf pulsar may cause material to be transferred from the companion star, forming an accretion disk that fuels the pulsar's emission. This process also raises questions about the long-term stability of such systems. Can a white dwarf pulsar survive for billions of years in a binary system, or will it eventually experience a catastrophic merger with its companion? These questions have implications not just for the life cycles of individual stars, but also for the dynamics of entire star clusters. One of the most intriguing possibilities in the study of white dwarf pulsars is their connection to the future of our own solar system. As the Sun ages, it will eventually shed its outer layers and leave behind a white dwarf. The fate of the Earth and the other planets is uncertain, but it is possible that in the distant future, the Sun's transformation into a white dwarf could produce similar phenomena to the pulsars we observe today. While the exact timeline for this is still billions of years away, the study of white dwarf pulsars can help us understand the long-term evolution of planetary systems, potentially giving us a glimpse of what our own solar system will experience as the Sun evolves. The discovery of white dwarf pulsars also raises broader philosophical questions about the nature of the universe. The more we uncover about the stars and remnants that make up our cosmos, the more we realize just how complex and dynamic the universe is. White dwarf pulsars, with their mix of magnetic fields, energetic radiation, and extraordinary lifetimes, serve as a reminder that even the quietest corners of space are filled with incredible phenomena that challenge our understanding of physics, time, and existence itself. The continued study of white dwarf pulsars will serve as a fascinating frontier for astrophysics. As technology advances, so too will our ability to explore the most enigmatic and far-reaching aspects of these cosmic objects. Each new discovery opens a window to deeper mysteries, forcing us to rethink long-held assumptions and imagine new possibilities. Whether it's through their energetic emissions, their role in binary systems, or their eventual fate as cold black dwarfs, white dwarf pulsars are sure to remain a central topic of inquiry for years to come. With the potential to revolutionize our understanding of stellar evolution, cosmic magnetism, and the fundamental laws of physics, white dwarf pulsars have much more to reveal. What we currently know is just the beginning, and as we continue to observe these extraordinary remnants of once vibrant stars, we can expect to uncover more hidden secrets about the universe and our place within it. As we continue to deepen our understanding of white dwarf pulsars, the potential for new discoveries grows. With each observation and theory, these stars become even more fascinating. Their ability to provide insight into the most extreme conditions of the universe, extreme magnetic fields, intense radiation, and the physics governing compact objects, makes them central to a variety of scientific endeavors. An important aspect of white dwarf pulsars is their connection to the broader context of stellar populations. Most white dwarfs are thought to arise from low to intermediate mass stars, and their pulsar counterparts add another layer to this picture. In studying white dwarf pulsars, astronomers can better understand the stellar mass function, which describes the distribution of star masses in a stellar population. By analyzing the pulsar's age, composition, and evolution, researchers can infer the mass of the progenitor star, helping to refine our models of stellar evolution. This understanding extends to the role of these stars in star clusters. White dwarf pulsars, as well as other white dwarfs, can provide valuable information about the dynamics of star clusters. The density of stars in clusters, combined with the gravitational interactions between them, may affect the formation of these pulsars and their evolution. As we study these interactions, we can gain insights into the environmental factors that influence stellar evolution, especially in dense stellar environments. One aspect of white dwarf pulsars that sets them apart from other types of pulsars is the role that their companion stars may play in their behavior. The binary systems containing white dwarf pulsars are crucial to understanding how these objects are powered. Many white dwarf pulsars are found in close binary systems, where one of the stars has evolved into a white dwarf, and the other remains a main sequence star or another type of compact object. The material transferred from the companion star to the white dwarf can generate high-energy radiation, including X-rays and gamma rays, which are detected as pulsations. The interaction between the two stars in such systems can also provide clues about the long-term dynamics of binaries and the fate of close stellar pairs. The role of accretion in these systems is particularly important. As material from the companion star falls onto the white dwarf, it forms an accretion disk, which can lead to the production of intense magnetic fields. These magnetic fields are what make white dwarf pulsars so distinctive. The pulsations emitted by these objects are a direct result of their strong magnetic fields and rapid rotation. This interaction also raises the question of whether white dwarf pulsars could eventually merge with their companion stars, either in a cataclysmic event or through gradual orbital decay. Such mergers could lead to a variety of outcomes, including the formation of new types of compact objects, such as magnetars or even black holes, depending on the masses involved. These mergers are not just theoretical. In fact, observations of binary star systems and the behavior of white dwarf pulsars have provided evidence of systems undergoing mass transfer and interactions. Some of the most spectacular events in the universe, such as supernovae and gamma-ray bursts, may be linked to such mergers or the collapse of a white dwarf into a neutron star or black hole. The study of white dwarf pulsars also contributes to our understanding of the behavior of matter in extreme conditions. The magnetic fields around these objects are strong enough to twist and distort the surrounding space-time, creating complex interactions between the stellar material and the emitted radiation. The conditions in these environments may resemble those found in the interiors of other extreme astrophysical objects, like neutron stars or black holes. Therefore, by studying white dwarf pulsars, we can learn about the physics of these extreme states of matter, including the behavior of plasma, the dynamics of magnetized fluids, and the interaction of radiation with matter. This research could also have implications for the field of quantum mechanics. The magnetic fields of white dwarf pulsars are so intense that they may induce quantum effects in the surrounding matter. Theoretical models suggest that under such extreme conditions, quantum electrodynamics, QED, could play a significant role in shaping the pulsar's behavior. Studying how these quantum effects manifest in the observable emissions of white dwarf pulsars could offer a new perspective on the interplay between quantum mechanics and general relativity, two of the pillars of modern physics. As we explore these pulsars and their associated phenomena, we are also learning more about the universe's history. The study of white dwarf pulsars allows us to probe the late stages of stellar evolution, shedding light on the future of stars like our Sun. These pulsars provide a glimpse into what our Sun may eventually become as it exhausts its nuclear fuel and transitions into a white dwarf. By understanding the physics governing these objects, we gain insight into the processes that shape the final stages of stellar life, not just for our Sun but for countless other stars in the galaxy. Moreover, the continued study of white dwarf pulsars could provide key clues to some of the most fundamental questions in astrophysics. One such question is the nature of dark matter. While white dwarf pulsars themselves are not directly related to dark matter, the extreme environments they create could potentially offer indirect evidence of the existence of dark matter. Some theories suggest that dark matter may interact with ordinary matter in subtle ways, such as through gravitational effects or electromagnetic interactions. By analyzing the behavior of matter in the vicinity of white dwarf pulsars, astronomers may be able to detect small deviations from standard models, offering new insights into the properties of dark matter. Additionally, these pulsars play a crucial role in the ongoing search for gravitational waves. The periodic motion of compact objects like white dwarf pulsars generates ripples in space-time known as gravitational waves. The detection of these waves could provide a new way to study the dynamics of these stars and their interactions with other objects in their systems. Gravitational waves carry information about the masses, distances, and velocities of the objects involved, and their study is rapidly becoming a central focus of astrophysical research. White dwarf pulsars also have the potential to inform our understanding of the larger cosmic web. These objects, often located in distant regions of the galaxy, contribute to the distribution of matter and energy in the universe. By studying their properties, astronomers can learn more about the structure of galaxies, the formation of star systems, and the evolution of the universe as a whole. Understanding the life cycles of white dwarf pulsars, their interactions with companion stars, and their eventual demise will help scientists piece together the larger story of cosmic evolution. White dwarf pulsars are among the most fascinating and enigmatic objects in the universe. Their combination of extreme magnetic fields, rapid rotation, and unique stellar evolution makes them a key subject of study for astrophysicists and cosmologists alike. As our observational tools continue to improve, and as we develop new theories to explain the complex physics behind these objects, the study of white dwarf pulsars promises to uncover even more about the universe's most fundamental processes. From the behavior of matter in extreme conditions to the detection of gravitational waves, the insights gained from these stars will continue to shape our understanding of the cosmos for years to come. And as we observe the mysterious dance of white dwarf pulsars, we are reminded that the universe is full of secrets waiting to be uncovered. The continuing investigation into white dwarf pulsars holds the potential to uncover new facets of astrophysics that have yet to be understood. With every discovery, researchers are building a more detailed picture of not only these fascinating objects themselves but also of the broader environment in which they exist. As technology advances and our ability to observe the universe in greater detail improves, the study of these pulsars is expected to expand in unexpected and exciting directions. One of the most intriguing aspects of white dwarf pulsars is their role as cosmic laboratories for testing theories of general relativity and quantum mechanics. Their strong magnetic fields and intense gravitational pull make them ideal candidates for studying the warping of spacetime, the bending of light, and the properties of matter under extreme conditions. These environments provide an opportunity to test the limits of our current understanding of the laws of physics. Astrophysicists and cosmologists have long sought to unify the theories of general relativity, which describes gravity at large scales, and quantum mechanics, which governs the behavior of particles at the smallest scales. White dwarf pulsars, particularly those in binary systems, offer a unique opportunity to study the interplay between these two areas of physics. For example, the way their intense magnetic fields affect the surrounding spacetime could provide a direct observational test for models that aim to unify gravity and quantum mechanics. By observing the pulsations, accretion disks, and other phenomena associated with these stars, researchers may uncover new insights into how these two branches of physics intersect. Another exciting avenue of research involves the study of the extreme environments around white dwarf pulsars. These stars produce intense radiation in the form of X-rays, gamma rays, and radio waves. The interaction of this radiation with the surrounding matter can lead to the creation of highly energetic particles and the development of complex plasma dynamics. The study of these particles, their behavior, and the way they interact with the strong magnetic fields of the pulsars could have broader implications for our understanding of the behavior of matter in extreme environments. This could eventually lead to advancements in fields such as nuclear fusion, materials science, and the study of particle accelerators. One potential breakthrough lies in the study of the inner workings of white dwarf pulsars themselves. While scientists have a general understanding of the physics that govern their behavior, much remains to be discovered about how they evolve over time. It is known that white dwarfs, in general, represent the final stage in the life cycle of low to intermediate mass stars. However, the processes that lead to the formation of white dwarf pulsars specifically, particularly those with magnetic fields strong enough to produce pulsations, are still not fully understood. One of the most compelling questions is how these stars generate such intense magnetic fields, and how they are able to maintain them over long periods. The role of companion stars in shaping white dwarf pulsars' behavior cannot be overstated. Many of these pulsars are found in binary systems, where material is transferred from the companion star to the white dwarf. This accretion process generates powerful emissions, including X-rays, and creates the conditions necessary for the formation of pulsar-like behavior. The interplay between the white dwarf and its companion star, whether a main sequence star, another white dwarf, or even a neutron star, can have a profound impact on the pulsar's evolution. Studying these binary systems offers valuable insights into the dynamics of star formation, evolution, and death. As researchers continue to refine their models and techniques for observing white dwarf pulsars, one thing becomes clear: these objects are far more than just fascinating celestial phenomena. They are key players in the ongoing effort to unravel some of the most profound mysteries of the universe. From their contributions to our understanding of the nature of matter and energy to their potential role in testing theories of gravity and quantum mechanics, white dwarf pulsars are rapidly becoming one of the most important subjects in modern astrophysics. In addition to their scientific importance, white dwarf pulsars also offer a glimpse into the future of stellar evolution. By studying these objects, scientists can gain a better understanding of what will eventually happen to stars like our own Sun. As our Sun nears the end of its life, it will shed its outer layers and leave behind a white dwarf. In some ways, white dwarf pulsars represent a preview of this future, albeit one that is more extreme due to the unique conditions involved. By examining these pulsars, we can learn more about the processes that will shape our own solar system in the distant future. The study of white dwarf pulsars opens up a multitude of avenues for discovery, touching on everything from the fundamental forces of nature to the future of stellar evolution. As we continue to observe these objects and improve our theoretical models, it is likely that we will uncover even more secrets about the universe and our place within it. White dwarf pulsars may be small in size, but their impact on our understanding of the cosmos is anything but. Whether through their role in testing theories of physics, their contribution to the study of dark matter, or their insights into the final stages of stellar life, white dwarf pulsars remain one of the most captivating and important phenomena in modern astronomy. As the exploration of white dwarf pulsars continues, it is essential to acknowledge the role that observational advancements are playing in revolutionizing our understanding of these enigmatic celestial objects. The methods used to study these stars have evolved significantly over the years, enabling scientists to peer deeper into their behavior, their magnetic fields, and the ways in which they interact with their environments. Through increasingly sophisticated telescopes and detectors, such as the Chandra X-ray Observatory and the Very Large Telescope, astrophysicists are able to capture unprecedented data that is shedding light on the many complex characteristics of white dwarf pulsars. The use of X-ray and radio telescopes has allowed for the detection of highly energetic emissions from white dwarf pulsars. X-ray observations, in particular, have been pivotal in identifying accretion disks around white dwarf pulsars, where material from companion stars is funneled toward the pulsar, producing intense radiation. This high-energy radiation is a hallmark of the pulsar's behavior, and by studying the spectrum of these X-rays, scientists can learn more about the temperatures and densities within these accretion disks. Radio waves, on the other hand, have provided another vital tool for observing pulsars in the far reaches of the electromagnetic spectrum. Pulsars emit a variety of radio pulses that can be detected and analyzed for patterns, which helps astronomers understand their spin rates, magnetic field strengths, and other key features. These radio signals can also be used to detect the presence of companion stars, measure orbital parameters, and study the density and distribution of interstellar matter in the regions surrounding these stars. One of the fascinating aspects of white dwarf pulsars is the fact that their radio emission patterns often differ from those of neutron star pulsars. Neutron star pulsars, which have stronger gravitational fields and more extreme magnetic environments, typically exhibit highly regular and predictable pulsations. In contrast, the radio emissions from white dwarf pulsars are often irregular, with variable pulse profiles. This has led to speculation that the mechanism behind their emission processes may be distinct from that of neutron stars, potentially pointing to the need for new models of pulsar behavior. The development of pulsar timing arrays is also helping to reveal new information about white dwarf pulsars. These arrays, composed of multiple radio telescopes positioned around the world, are able to detect and measure the arrival times of pulsar signals with unprecedented precision. By comparing the timings of these signals across different locations, researchers can detect subtle variations in the pulsar's motion, which can then be used to study the characteristics of its companion star, its magnetic field, and its environment. These observations provide invaluable data on the orbital dynamics of binary systems, the nature of accretion processes, and even the effects of general relativity. An important question that continues to captivate astronomers is how white dwarf pulsars, particularly those that are part of binary systems, are able to generate and maintain their strong magnetic fields. Magnetic fields in these stars are believed to be formed during the early stages of their evolution, but how these fields persist and evolve over time remains a mystery. In the case of white dwarfs, their magnetic fields are thought to be generated by the motion of electrically charged particles in the stellar interior. This process, known as the dynamo effect, is responsible for creating the magnetic fields in stars. However, the exact mechanisms by which the fields are sustained in white dwarf pulsars, especially when compared to those in neutron stars or other types of white dwarfs, remain unclear. Some scientists have proposed that the intense magnetic fields of white dwarf pulsars could be a result of interactions with their companion stars. In a binary system, material from the companion star can be accreted onto the white dwarf, and this accretion process might help amplify or enhance the magnetic field. This idea has gained traction as researchers observe that many of the most powerful white dwarf pulsars are located in binary systems where accretion plays a significant role. The exchange of matter between the stars could also influence the rotation rates of the pulsars, which would, in turn, affect their emission patterns and the characteristics of their magnetic fields. Theoretical models suggest that the strong magnetic fields of white dwarf pulsars could also be related to the interaction of the star's interior structure with its outer layers. For instance, as the white dwarf cools and contracts over time, the material within the star becomes denser, and the magnetic field could become more concentrated. This would create a more powerful magnetic field that could result in the pulsar-like behavior observed. Additionally, it's possible that the field may undergo complex processes that cause it to become more chaotic, or even flip over time. This would have profound implications for the way that white dwarf pulsars generate their radiation and interact with their environments. One of the most intriguing aspects of white dwarf pulsars is the possibility that they might reveal new insights into the behavior of matter under extreme conditions. White dwarfs are already known for their unique properties, such as the degenerate matter that makes up their interiors. This matter, which consists of electrons that are packed into an extremely dense state, plays a crucial role in preventing the white dwarf from collapsing under its own gravity. However, little is known about how the material in a white dwarf behaves in the presence of such strong magnetic fields. The magnetic fields could significantly alter the properties of the degenerate matter, creating new phenomena that are not present in non-magnetic white dwarfs or in other types of stars. These extreme conditions offer an opportunity to study the behavior of matter under pressures and temperatures that are unattainable in laboratory environments on Earth. The study of white dwarf pulsars may also have important implications for our understanding of stellar evolution. As mentioned earlier, white dwarf pulsars are the remnants of stars that have exhausted their nuclear fuel. Understanding how they evolve and what conditions lead to their transformation into pulsars can provide valuable insights into the life cycle of stars, especially those that are similar in size to our Sun. These objects are the final stage in the life of such stars, and they provide a glimpse into the future of our own solar system. By studying the behavior of white dwarf pulsars, scientists can begin to piece together the fate of stars that undergo similar processes. Looking to the future, there is a strong possibility that advances in technology and observation methods will lead to even more discoveries about white dwarf pulsars. As telescopes become more sensitive and capable of detecting a wider range of electromagnetic radiation, astronomers will be able to study these stars in greater detail than ever before. New theoretical models will also be developed to explain the complex phenomena associated with these pulsars, potentially unlocking secrets about the fundamental nature of the universe. Moreover, the continued study of white dwarf pulsars will likely have broader applications beyond just the field of astrophysics. Understanding how extreme magnetic fields and gravitational forces interact with matter could have profound implications for other areas of physics, such as the study of high-energy particle collisions and the development of new materials for use in advanced technologies. The lessons learned from these cosmic objects may one day influence the way we approach problems in fields as diverse as materials science, quantum computing, and even energy generation. Ultimately, the ongoing research into white dwarf pulsars represents a frontier in our quest to understand the cosmos. These objects, though small in size, contain vast amounts of information about the nature of matter, energy, and the forces that govern the universe. As we continue to explore the mysteries surrounding these pulsars, we move closer to unraveling the secrets of the universe itself. As the research into white dwarf pulsars advances, one of the most pressing questions that astronomers seek to answer is the origin of their distinctive emission patterns. The radiation emitted by these pulsars often exhibits unique signatures that distinguish them from other types of stellar remnants, such as neutron stars. Understanding the precise mechanisms behind these emissions is crucial for expanding our knowledge of how these celestial objects work. The radiation emitted by white dwarf pulsars is not only highly energetic but also often irregular in its pulsation patterns. While neutron star pulsars typically produce regular, predictable pulses, the signals from white dwarf pulsars can vary significantly, sometimes showing irregularity in pulse timing or frequency. This behavior has led scientists to explore the possibility that the mechanisms responsible for generating these emissions might differ significantly from those in neutron stars. One of the key features that sets white dwarf pulsars apart is their lower mass and relatively weaker gravitational fields compared to neutron stars. This may mean that the energy processes occurring within white dwarf pulsars are fundamentally different. One of the hypotheses put forth to explain the emissions from white dwarf pulsars involves the complex interactions between the pulsar's magnetic field and the accretion disk surrounding it. As material from a companion star is drawn toward the white dwarf, the intense magnetic field of the pulsar could channel the accreted material along magnetic field lines. This process can lead to the formation of hot spots on the pulsar's surface, where the material, in the form of highly energetic particles, collides and releases radiation in the X-ray or radio spectrum. In some cases, the pulsar's magnetic field may even become twisted due to the accretion of material, leading to the emission of non-sinusoidal signals and adding to the irregularity of the pulsar's pulse pattern. In addition to the magnetic field, the rotation rate of the white dwarf pulsar plays a crucial role in determining the nature of its emissions. White dwarf pulsars are typically fast rotators, spinning at rates much higher than those of ordinary white dwarfs. As these stars spin, their magnetic fields can distort and generate powerful bursts of radiation. This rapid rotation can create highly concentrated areas of electromagnetic energy on the surface of the pulsar, resulting in irregular bursts of X-ray or radio waves. These bursts can be detected by ground-based and space telescopes, providing scientists with valuable data on the pulsar's internal structure and its behavior over time. Another fascinating aspect of white dwarf pulsars is the discovery that they can exhibit behavior similar to that of certain types of millisecond pulsars, a class of neutron stars that rotate exceptionally rapidly. The analogy between these two types of pulsars lies in the fact that both may have gained their high rotation rates through the process of accretion from a companion star. In the case of white dwarf pulsars, it is believed that the material from a companion star falling onto the white dwarf's surface can cause the star to spin faster, effectively transforming it into a pulsar. This process is known as spin-up, and is a critical aspect of the evolution of both white dwarf and neutron star pulsars. The spin-up process is particularly relevant to white dwarf pulsars that are part of binary systems. These systems, in which the pulsar is paired with a companion star, are thought to play a crucial role in the evolution of these objects. Over time, the material from the companion star is transferred onto the white dwarf, increasing its mass and altering its angular momentum. This can cause the pulsar to spin at increasingly faster rates, eventually reaching the high speeds that characterize white dwarf pulsars. While much is still to be learned about the spin-up process in white dwarf pulsars, there is growing evidence that this mechanism may play a significant role in the overall evolution of these stars. By studying the mass transfer rates and the timing of pulses from white dwarf pulsars, astronomers can gain insights into how these systems evolve over time and how they contribute to the overall population of pulsars in the universe. Interestingly, the study of white dwarf pulsars may also reveal unexpected connections to other areas of astrophysics. For instance, the interaction of a pulsar's magnetic field with the surrounding environment may help to answer important questions about the nature of magnetic fields in general. Understanding how white dwarf pulsars generate and maintain their strong magnetic fields could provide valuable clues about the behavior of magnetic fields in other astrophysical objects, such as galaxies, black holes, and neutron stars. In addition to the implications for stellar evolution and magnetic fields, the study of white dwarf pulsars also has the potential to enhance our understanding of gravitational waves. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, and they are often associated with cataclysmic events like supernovae and the merger of black holes. However, it is now thought that certain types of pulsars, including white dwarf pulsars, may also emit gravitational waves. The detection of these waves, which is possible using highly sensitive instruments like LIGO and Virgo, could open a new window into the study of the universe. White dwarf pulsars could emit gravitational waves due to their rapid rotation and strong magnetic fields. As the pulsar spins, it could create distortions in spacetime, producing detectable gravitational waves. The detection of these waves would not only provide valuable information about the internal dynamics of white dwarf pulsars but also serve as a unique probe into the fundamental nature of spacetime itself. The potential for studying gravitational waves from white dwarf pulsars is an exciting area of research, and it could provide new insights into both the behavior of these stars and the nature of gravitational physics. Looking ahead, there are numerous exciting developments on the horizon that will further enhance our understanding of white dwarf pulsars. One of the key goals for future research is to improve our ability to detect and analyze these objects in more detail. As mentioned earlier, Advanced telescopes like the James Webb Space Telescope and the Square Kilometre Array are expected to provide unprecedented capabilities for studying pulsars and their associated phenomena. These new observatories will be able to observe pulsars at higher resolutions and across a wider range of wavelengths, allowing astronomers to gather more comprehensive data on their emissions, magnetic fields, and companion interactions. Moreover, the study of white dwarf pulsars could also have profound implications for the search for life beyond Earth. Pulsars, in general, are often used as tools for probing the interstellar medium, as their radio signals can be used to measure the density of matter in space. This ability to map the structure of the universe on large scales is one of the key reasons why pulsars are such valuable objects for astronomical research. By studying white dwarf pulsars, astronomers can gain a better understanding of the distribution of matter in the galaxy and the nature of the interstellar medium, which could, in turn, inform the search for extraterrestrial life. In conclusion, the study of white dwarf pulsars is a captivating journey into the heart of stellar evolution, magnetic phenomena, and gravitational physics. These stars, though small in size compared to other stellar remnants, offer a wealth of information about the forces that shape the universe. From their unique emissions to their potential for generating gravitational waves, white dwarf pulsars are at the forefront of modern astrophysical research. As technology continues to advance, our ability to study these enigmatic objects will only improve, bringing us closer to understanding the intricate details of their behavior and their role in the cosmos. The mysteries of white dwarf pulsars are far from being fully unraveled, but the quest to unlock their secrets is a journey that will undoubtedly continue to captivate and inspire future generations of astronomers and scientists. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.